Hey guys, so we just finalized the solution for the lane segmentation problem. And now what's the next step? If you look at the output of the lane segmentation, you can clearly see that the outer lanes were being clearly segmented out, but the mid lane were giving us a box patched result. The reason for the box patched result of the mid lane segmentation was that the mid lane were already box patched in their RGB form. So how can we connect this box patch mid lane to get the actual boundary representation of the mid lane? This problem is known as estimation. If you look on the screen, you can see that there is an image that is the actual output of the mid lane segmentation. The mid lane segmentation image shown right here has in the middle the box patch representing the mid lane, and on the top shown right here is the false positive contour being detected as the mid lane. What we want our estimation algorithm to do is connect these box patches right here so that we get the actual boundary representation of the mid lane. And we don't want this estimation algorithm to connect any box patch mid lane to any false positive present there. This will lead to inconsistent results. This problem can be solved through multiple approaches, and let's look at a few of them. Hi guys, so we just finished testing the first approach of estimation of the mid lane, that was using the huff lines. But huff line provided us with many inconsistent results. So the next step for me was to test out the other function in OpenCV that perform the estimation of trajectories. But they were proving to be very complex and using a lot of computational power. So the next obvious step for me was to design my own algorithm for this problem, and let's see what happens. So the algorithm is shown right here. So starting with this first image, let's call it image 1. This is the output of the mid lane segmentation process. And shown right here is the error or the false positive in the mid lane segmentation. And shown right here is more of that false positive results. And shown right here is the mid lane patches being segmented up. So the first step was to reject the contours that are less than the threshold area. This proved to remove all the small contours like here and here, but still left us with this contour as it was larger than the threshold area. So the next step was to connect all the contours that are closer than the minimum distance. For example, all the mid lane patches like right here will get connected, but this contour right here will get disconnected with the mid lane patch as it is farther than the minimum distance. So after applying this step, which proved to be a crucial step, we get the largest contour being the mid lane patches being connected to each other. So the last step was obvious, to keep the largest contour as it was the mid lane estimated trajectory. Now this solution proved to be very effective, more effective than the huff line estimation algorithm. So let's look at its code flow. For coding, our input will be segmented mid lane, which is in patches. And we want the mid lane trajectory estimated as an output, something like this. So let's code this. In the previous training session, we were able to perform lane segmentation on the basis of color, but there was a problem in the output of mid lane segmentation. We never got the complete mid lane trajectory estimated. To get to the region where the car needs to be, we require the complete mid lane and the complete outer lane. As you can see, the output of mid lane segmentation gave us this box patch result. Our main target in this training session is to estimate the mid lane trajectory given the box patches. This can be done by following the method described in the theory for estimating the mid lane. For this purpose, I've created a new file that is midlaneestimation.py, and inside it I've declared the function of estimate mid lane. And here it takes in two inputs. The first is the mid lane patches, that is the output of mid lane segmentation, and this will become the input of this function. The second argument is the max distance. Basically, this is the distance that describes any two patches to be part of the same mid lane or some foreign object. Starting with the first step, that is to keep a mid lane draw for displaying the shortest connectivity later on. So we need to create a mid lane draw BGR color space image in which we can draw the connectivity for the complete mid lane trajectory. So we use the CV2.convertColor and provided the mid lane patches as the source. Then we provide the code of CV2color, that is gray to BGR, as we are converting from grayscale to BGR. And the output that we get, we name it mid lane connectivity BGR, as it is in BGR color format. This particular image will be used later on to draw the connectivity between the patches. Now once we have that, the next step is to extract the contours that define each object. These contours can be extracted using the OpenCV function of find contours. It requires the image from which we are going to extract the contours, that is the mid lane patches. Then we provide the mode, that is CV2 retrieve list, which simply retrieves the contours in the form of a list. The third argument is the method, which I'm going to write as CV2 chain approximation simple. This simply extracts the simplest most contours that define any object. And then I will simply take the first output of this function, that is simply the contours that have been extracted, and I name it contours. Once I've done this, we move on to the step 3, that is keep only those contours that are not line. Now contours can be of any object that might be point, lines, or any other shape. We only require those objects that are larger than a specific area. So we define a specific area, that is minimum area, as 1. So if any object has an area larger than this minimum area, then that object is our required object. So for that case, we keep an account of all the legit contours that have an area larger than this minimum area, and that legit contours will be stored inside this list. Then we simply iterate over the contours that we have by writing for, ignoring the first value, and then extracting the contour in enumerate, and then providing the contours. Now once we loop over all of these contours, we extract the area by CV2 contour area. We provided the contour And the area that we got, let's name it contour area. And once we have the contour area, we can now compare it, like if contour area is greater than the minimum defined area, then that contour is part of the legit contours. So we simply append it to the legit contours. And once we have done that and done with all the loop, all of the legit contours are inside the list of legit contours. Then we can simply replace the contours with these legit contours, thus discarding the non-relevant contours. Then we can proceed to the next step, that is to connect each contour with its closest. Now, if you remember, our main goal in this particular algorithm was to connect the box patches with each other so that we can get the complete mid-lane trajectory estimated. To do that, we require two separate loops, both iterating over the contours, but in different indices. So we do that, we define our loops and start extracting the candidate ID best match. Now the candidate ID best match here is simply the best match to each particular contour. So which contour is closest to a specific contour? We start by iterating for the first index or the first contour, find its best match, and then move on to the next contour. And we do the same procedure till we have done or found every contour that is closest to each contour. And this means we have found the closest match, and we can simply connect that particular contour with its closest, and thus completing the mid-lane trajectory that we opted for in the beginning. Once we have this, we have extracted the contour and contour compare by simply looping over its indices. We can now compare or simply find the minimum distance between each of these contours. So we start by finding the minimum distance between the two contours we are currently iterating through. So for that, we need to create a new function. That function is approx distance between centers or contours. This function finds the approximation distance between the two contours. Now, if we provided the contour from the outer loop, we provided the contour from the inner loop, and try to compare both of these contours by extracting their moments, the centroid, and then comparing the distance by finding the distance between the centroid. And once we have that, we can say that this is the minimum distance. We have the centroid of the first loop or the first contour and the centroid of the second contour as the three outputs. So we simply call this function. Right after we have simply declared the two loops, inside it, the first if condition that we declare is that we do not want to compare any contour with itself. So we simply say if index is not equal to index compare. So we don't want to compare any contour with or any patch with itself. Once we write this, we go inside it and simply call that particular function that we have declared above. That is to find the distance between two contours. We pass in the first contour, that is the outer loop contour, and pass in the second contour, that is the inner loop contour. And what we get as an output are the minimum distance between these contours. Then we get the centroid of the first contour and the centroid of the second contour. Once we have these values, we can simply check if this minimum distance that we have just found between these contours is less than the previous minimum distance. Now, I have not mentioned this before. I've declared these four variables. Now, these four variables will become useful later on when we try to compare or find out the minimum distance or the minimum distant contour for our particular contour that is happening inside the outer loop. So the minimum distance or the previous minimum distance will be stored inside this variable. The best index, that is the closest contour index, will be stored inside this variable. And the best centroid A and the best centroid B will be stored inside these variables. Starting with the previous minimum distance, which is initialized to 100,000, we compare it with the minimum distance that we have just found for this contour compare, that is the current contour. We simply check if the current minimum distance is less than the previous minimum distance. If that is the case, then we have found a contour that is closest than the previous closest found contour. Then what we simply do, we check if we have already found the closest contour or not. That can be done by simply checking the length of the candidate ID best match. Now, candidate ID best match is a list that contains all the best matches for that particular contour. Now, if the candidate ID best match is equal to 0, then that means that we have not found any closest contour for any particular contour or any particular patch. That means that we can simply add in or update our previous minimum distance and all of the rest of the four variables that were declared above. That means previous minimum distance get equal to the minimum distance. In the same way, the best index compare equals to the current index compare. In the same way, the best centroid A gets equal to the current centroid A. In the same way, the best centroid B gets equal to the current centroid B. Once we have updated these values, we need to cater for the else condition where that candidate ID best match list is not equal to 0, meaning we have previously found closed contours to 1, 2, 3 to x values. Now, if that's the case, we need to loop over each of these values in that candidate ID best match and then try to find if such a combination was found before. If such a combination was found before, then we need to simply ignore that combination because that connection with the closest contour has already been made. So we need to create a Boolean variable that we name as already present, that is combination already present. We start by initializing it to false and then loop over that particular candidate ID best match list by writing for I in range length of the candidate ID best match. Now, when we try to do that, then we simply given the condition that checks if that particular combination that we have found right now as the closest contour match has been found before. If it has been found before, then we simply ignore this combination because that connection has already been made. Otherwise, we simply update this connection. Now, this particular if condition simply checks if that particular combination was present before or not. If it was not present, if it was present, we simply say that it was already present as true. Otherwise, if not already present, we simply update the previous minimum distance, the best index compare, best centroid A, and all of the rest of the values. Now once we've done that, and once we have updated all these values, then we can simply move in back to our inner loop that was for the index compare. Now here what we need to do, because we have found the closest contour for any particular contour of the outer loop, all we need to do is simply check if that closest contour is beyond that minimum distance or beyond that maximum distance or not. If it is beyond the maximum distance or maximum allowed distance that was declared in the second argument of our function, then we simply discard that particular contour. And that can be done by simply writing if the previous minimum distance that we have just found is not equal to 100,000, and if it is not equal to 100,000, that means it's the same value, and the previous minimum distance is greater than the max allowed distance, then that means we need to simply discard this value and not make any connections. If that is not the case, then we simply check if whatever contour that we have found is a legit contour. If that is a legit contour, that can be checked by writing if type best centroid A is not equal to int. If you remember, we have initialized this best centroid A with an integer, but whenever we find the best centroid, then that's going to be a tuple. So if it is still an integer, then that means that we have not found a best centroid that is the closest match to that particular contour. That means we need to update or simply make that connection. That can be done by first updating the candidate ID best match by candidate ID best match dot append, and then writing here the best index compare that we have found previously. The next thing that we need to do is simply create a connection by writing CV2 line, providing it the image of mid-lane connectivity BGR, taking the point 1 as best centroid A and connecting it to best centroid B that we have found previously, giving the color as green by 02550 and thickness as 2. Once we have done this, we have simply created a connection from a particular contour to its closest contour. Once we have done this, and we have done this for all of the loops, that is the outer loop, then we can simply move on. To simply converting this BGR of connectivity back into grayscale so that it can be output. So to convert it into grayscale for later usage, all we need to do is use CVT color, provided this mid-lane connectivity BGR, and write CV2 color BGR to gray. This converts it back to gray, and we give it the name of mid-lane connectivity without the BGR. Now this is in grayscale right now, and now we can proceed to the next steps. Now at the moment, what you will notice is that we have done a lot of steps that has led to us to this mid-lane connectivity. Once all the inner and the outer loop has been completed, we will get all the connections done between the mid-lane patches, and any other noise will simply get disconnected. So all that is left for us to do is simply get estimated mid-lane by returning the largest contour, because that will be consisting of the estimated mid-lane. And that can be done by creating a new function that simply returns the largest contour. So we have created a function that simply returns the largest contour along with whether that largest contour was found or not. We simply call it right in this fifth step, that is CV2 return largest contour, pass in the mid-lane connectivity that we have just converted to grayscale, and what we are left with is simply the estimated mid-lane and a boolean representing that largest was found or not. Now if the largest was found, give it the name of estimated mid-lane. Now the sixth step is simply return the estimated mid-lane if it was found, otherwise stand original. So if the largest is found, then all we need to do is simply return that estimated mid-lane, because we have found the estimated mid-lane trajectory. Otherwise, if we were unable to do so, we simply return the original mid-lane patches. Now, that can be done by simply writing if largest found, return estimated mid-lane, else simply return the mid-lane patches. So this completes our process of estimate mid-lane. And once we have done this, we have completed the process or the second step of our lane detection module. Now all we need to do is go inside the lane detection module and simply call this estimate mid-lane function. And that can be done by simply importing that particular function by writing from dot b mid-lane estimation import estimate mid-lane. We go after this display functions, or before this display function, simply calling the estimate mid-lane, pass in the mid-lane edge, and then what we get as an output is simply the estimated mid-lane. Now once we get this, all that is left for us to do, another thing that we need to pass is the mixed maximum distance, and that is part of the config max distance resize. So once we have done this, we can simply display whatever estimated mid-lane that we got back, and that can be done by simply adding in a new IAM show of CV2 IAM show estimated mid-lane and then enter. Once we have done this, then this particular process will run flawlessly at this moment. And then all we need to do is simply include this particular package inside setup.py. Now once we build this package again, to see whether this has taken effect or not. Once you have done this, we run the simulation again, and then run the computer vision node again. All right, the numpy is not defined, so we need to import the numpy. All right. So import numpy as np. Now once the error goes away, we can build this again, run the simulation again, and then run the computer vision node again. Whoops. So there was a problem in declaring this estimated mid lane. I was just calling the function again. So once I do that, get rid of the error, save it, build our call build, run the simulation again, run the computer vision node again, and what we get as output, this is the mid lane segmentation, this is the mid lane mask, mid lane edge, and this is our estimated mid lane. And as you can see, the mid lane patches have been perfectly connected with each other. So we have finally completed our second step of the lane detection module that was estimating the mid lane trajectory from the given mid lane patches. Now we can proceed to the third step and get even closer to getting the final outputs of our lane detection module. Till then, thank you and bye. Hi guys, so we are ready to turn to the third and the final stage of the lane detection module, that is the cleaning stage. Now cleaning stage comprises of two steps, for the first step being the removal of the incorrectly predicted outer lanes. Now shown right here, on the left hand side is the frame 1 and on the right hand side is the frame 2. Now both these frames were being extracted from the Raspberry Pi cam video taken in different intervals of time. Now segmenting the frame 1 for the outer lane, what we would get is this right segmented lane and this left segmented lane, which is probably the correct right and the left outer lane in the frame 1. Now processing this further would result in getting us the final outer lane, that is the right outer lane. Now the question would arise whether this outer lane that is the final outer lane was the correct one, or whether this outer lane was of our interest or not. To understand or answer this question, we need to look back at the frame 1. Here we can see that the right hand side of the road is probably the larger of the two sides, which would suggest that the car is probably on the right hand side of the road. So this means that we are interested in the middle lane and the right outer lane to use them both to predict the probable road path. So this means that our predicted outer lane is probably the correct one. Now let's look at example 2 or frame 2 of this stage. This here is another frame. So looking at this frame, you can see that the only visible outer lane is the left hand outer lane. So segmenting based on yellow color would only give us back this left outer lane as the segmented outer lane. And processing this further would only break this down further into two boundaries. Now, the same question would be asked whether this outer lane that is predicted or the final outer lane, is this the correct one? To understand or answer this question, we will again go back to the frame 2, where we will observe that which side was the larger. So right here you can see that the right hand side of the road is the larger of the two sides, which would suggest that the car is probably somewhere right about here. So the lane lines that we are interested in is the mid lane lines and the right outer lane. So what this means is that our predicted outer lane for this particular example was the incorrect one. So the goal for this particular step of the cleaning stage is correct for the incorrectly predicted outer lanes. Hi guys, so we just discussed the step 1 of the cleaning stage, and now we are ready to take on the step 2, that is extension of the lane lines. Now for this explanation of step 2, I've laid down two examples for you, and let's start with example 1, that is frame 1 on the left hand side of the screen. Now the first output that you see right here is the step 1 output of the cleaning stage. Inside it you can see the mid lane and the outer lane being segmented out. Now if you look closely at the outer lane, what you will notice right at the bottom is that the outer lane was not touching the ground. This means that it was an incomplete outer lane, as the middle and outer lane both have the same length. So if you use these particular lane lines to calculate the road path, what you would get is an incomplete road path estimation. And that can lead to a lot of problems, because using this incomplete road path will get us an incorrect road center estimation than the actual road center. So what we would ideally want is to extend the lane lines of where they are incomplete. Like for example, in our case, the outer lane line was incomplete, so we will calculate its slope and extend it in the direction of the bottom, so that we get the complete road path estimated. Now let's look at the second example to get a better idea of what I want to achieve in this particular step right here. Now the first output that we get is the middle lane and this drawn outer lane. Now the drawn outer lane has the same height as the middle lane and is touching the ground, but the middle lane is not touching the ground. So if I use these lane lines to draw the probable road path, what I would get is an incomplete road path estimation. So what I would want is to extend the lane lines of which are incomplete. For example, right here I have the incomplete middle lane. So I will extend that middle lane to touch the ground, so I get the complete road path estimated. So this was the theory behind the step 2 of the cleaning stage, and now we will discuss its code flow. For coding the step 1 of cleaning stage, we will be requiring the segmented outer lane as an input. In a sense, we are required to correct for the incorrectly predicted outer lane and also keep its inner side, something like this in this case. In the coding section of cleaning stage step 2, we will get the estimated mid lane trajectory and the corrected outer lane as an input, and what we require for an output are the complete lane lines by extending them towards the bottom. For the following case, this will be our output. Hi. Previously, we were able to extract the complete mid-lane trajectory from the given mid-lane patches. This meant that at this moment, we are somewhere here. Now, before moving on to extracting the useful information about the car trajectory and the lane path, we need to perform a little bit of cleaning first. This can be done in 2 steps. For the first step, we need to retrieve the side of the outer lane which is closest to the mid lane, also correcting for the incorrectly predicted outer lane. Apart from this, for the second step, we need to extend the mid lane and the outer lane so that they both originate at the image bottom. This is where the car is. For this purpose, I've created a new file that I have named as ccleaning.py file. Now, this particular file will implement the third step in the lane detection module. Inside it, I've declared a function that is getYellowInnerEdge. It takes in 3 arguments of outer lane, mid lane, and outer lane points. Using these arguments, this function will try to implement the first step of the cleaning stage, that is, to retrieve the inner side of the outer lane, also correcting for the incorrectly predicted outer lane. Starting off with this first step, that is, to simply extract the contours that represent the mid lane and the outer lane. And that can be done in OpenCV by using a simple function of findContours. Once we have found the contours that actually represents both the mid lane and the outer lane, we can proceed to the next step. For the next step, what we need to do is to simply check if the outer lane was present initially or not. Now, if the outer lane was present, we keep that into account by storing a Boolean variable that stores the information that the outer lane was present before or not. This might come handy later on. Moving on to our next step, what we have is this, that we need to extract or take a random point from our estimated mid lane. Now, this random point will be used to estimate or check whether a given outer lane is the correct outer lane or not. How this is going to be used will be explained later. So we extract that particular point from our mid lane. Then, moving further, we will check whether we have the 2 outer lane points that are required to check or find out the inner side of the outer lane. Now, if we have the 2 points, for example, if we look at this case where we have this red side and this orange side, so we definitely have the 2 points representing the 2 sides of the outer lane in this particular case. Now, we want to find out which of these sides is closest to the mid lane, because that along with the mid lane will constitute to give us the road path in which the car can move. So, writing the equation or writing the steps for this particular case, we need to check which of the points in these 2 points is closest to our reference point. Now here, we use the function of distance, which is a part of the utilities.py. So we need to import it from utilities. Import distance. Also, we also import coordinate sort that might come handy later on. Here, what you will observe is that whichever side is the closest is drawn on a new matrix variable that is outer lanes return. Now this will be created by the same outer lanes, but instead it will be empty at the moment. And whenever we retrieve the correct outer lane, it will be drawn on this particular matrix. Now, once we have drawn that particular matrix and retrieved its contours, we can proceed to the other case. Now, once we have find out the correct outer lane, then what we need to do is the green outer lane. Then what we need to do is simply check if that particular outer lane is the correct one or not. If it was incorrectly predicted, then we need to correct it. But first, we need to check whether this was the correct outer lane or not. And the method that we use to check whether the outer lane is correct or not is this particular method that is shown in this image. What we do is simply draw a line from the image center to the lower point of the road trajectory. And the road trajectory is made from the center point or average point of our mid lane and the outer lane. Now, for the upper case, if the outer lane is on the right-hand side of the mid lane, then the trajectory points lies in the middle of both these lane lines. Now, if right here, which is closest to our image center. Otherwise, if the outer lane was on the left-hand side of the mid lane, in the same case, then the trajectory point will be on the left-hand side of the mid lane, and drawing a line from the image center to the trajectory point, to the trajectory lowest point, will intersect the mid lane at some point. This will indicate that this particular outer lane is the incorrectly predicted outer lane, or not representing the outer lane, which constitutes to give us the correct road path. So this particular function can be implemented right over here, and we name it as isPathCrossingMid. Once we have implemented this, it will return 2 variables that are Boolean variables. The first is that it returns whether it was passing mid or not, or whether it was crossing mid or not. If it was crossing mid, indicates that that was an incorrect predicted outer lane. And this also returns whether it was crossing it from the left-hand side or from the right-hand side. If it was crossing from the left-hand side, then that means that the correct outer lane will be on the right-hand side. Now, once we have implemented this function, we need to call it simply this way. We provided the mid lane, mid contours, and the outer contours return, and what we get are the 2 Boolean variables. Now, if the path is crossing, what we simply do is simply outer lanes 0 the outer lanes, because that is an incorrectly predicted outer lane, so we turn that to an empty image. Otherwise, we simply return whatever that we have, that is outer lane, and mid contours. Proceeding further to a second case where the outer lane points are not equal to 2. So there can come a case where the outer lane are present, but their points are not 2 in number. This means that we cannot estimate which side is the closest. So what we simply do is basically only check whether it was crossing mid or not, indicating the correct or the incorrect outer lane. So for that particular case, we simply check that if outer lane were present or not, and then check if it was crossing mid or not. If it was crossing mid, we empty that outer lane, otherwise return everything that we have. Now proceeding to the next step, that is, understand the case if there was no outer lane present. Now this can happen in two ways, or in two cases, whether it was present before and it was completely wiped out because of being incorrect, otherwise it was not present altogether. So we need to cater for this case. So we cater for this case by writing the condition where the outer lane is not present. Then we sort our mid lanes and then get the lowest point of the mid lane contours. Then moving on, we address which side to draw the correct outer lane. Now once we have identified which side is the correct side to draw the outer lane, we then draw that outer lane. And that can be checked in two cases. If the outer lane was present before, then it means it was wiped out because of being incorrect. So whichever path it was, whichever direction it was, is the incorrect direction, and we need to go to the opposite direction. And if it was not present, then what we simply do is compare the mid lane and which side it was to our image center. If the mid lane is on the left-hand side of the image center, then we draw on the right, otherwise we draw on the left. So using this information, we proceed to draw our correct outer lane, which will look something like this in this case. Because the mid lane is on the left-hand side, the outer lane will be drawn on the right-hand side, and it will be of the same height as the mid lane. Now once we have drawn the correct outer lane, we simply retrieve its contours and then return everything that we have. That is the new correct outer lane, its correct contours, and then return the contours along with the mid contours. This will also retrieve us the offset correction, because we also have the offset in this case, because we do not have the actual outer lane but only the estimated outer lane. So we have to set a variable that is named as offset to cater for that error. Once you have done this, then we look at the case where there was no mid lane at all. If there was no mid lane at all, then what we simply do is return everything that we have at the initial state. At the moment, the offset correction has not been declared globally, so we need to declare it at the start. We simply set it to 0 and then proceed to the next step. Once we have done this, we have returned or defined our first step in the cleaning state. We can proceed to the second step, that is extending both the mid lane and the outer lane so that they both originate at the image bottom. This will be named as extend short lane, because we are basically extending the short lane, whichever of them is short. Proceeding further, we start off by first sorting out our contours if they were present, and then retrieving how many contours that we have present at the initial point. Once we have the total number of contours for the mid lane and the total number of contours for the outer lane, we can proceed to the next step. The next step is simply extend the mid lane, which will look something like this. Because our mid lane is already connected to the image bottom, we don't need to extend it any further. This can be done using the function of lines. Then proceeding further, to cater for the case for extending the outer lane, which will look something like this. Now here, as you can see, the outer lane was not connected to the image bottom. So first what we do is simply extract the slope by using the last few points of the outer lane and then extending it in the direction of the slope. So starting with extracting the last few points of our outer lane. Once we have extracted the last few points, then we can use those few points to simply extract its slope. Once we have extracted the slope, we can then use that slope to extend it towards the image bottom. Then we can simply extend it using the function of line. Once we have extended it towards the image bottom and it still does not connect it to the image bottom, then we can need to cater for that case and then extend it by drawing a vertical line from the last point of the outer lane to the image bottom. This eventually connects it towards the image bottom, finishing our case, and then we can simply return it as a return mid lane and the outer lane. Once we have extended both these cases, all that is left for us to do is simply declare it in the lane detection module by calling it with the required arguments. So we need to import it from our C cleaning. Import both these functions representing the two sides, that is get yellow inner edge and extend short lane, and then simply I'm showing whatever that we have retrieved. The two things that we got, or the three things that we got, is the outer lane one side, extended mid lane, and the extended outer lane. Once you've done this, we can now build it. It builds successfully, launch the simulation file, run the computer vision node, and then we get our outputs. And if you remember, what we get as the first output is the outer lane one side. Then what we have is the extended mid lane and the extended outer lane. As you can see, the outer lane has been extended towards this direction of the image bottom. Now we have implemented the cleaning steps. Now our both mid lane and the outer lane are both correct and also complete, so that we can move towards extracting the useful information from both these lane lines. Till then, thank you and bye. Hi guys, so we are finally ready to talk about the data extraction in the lane detection module. But before that, I would like to discuss what we have achieved so far in the course. So shown right here is the frame extracted from the video taken by the Raspberry Pi cam. Now from this particular frame, we were able to extract two things. The first one being the middle lane shown on the left-hand side of the screen, let's call it M, and the second one being the outer lane shown on the right-hand side of the screen, let's call it O. Now these M and O were combined to make a thing known as lanes combined, shown right here. Now from these lanes combined, we were able to estimate the probable road path. Now this probable road path is composed of a lot of points. Let's call these points as trajectory points. These trajectory points can be computed from the lane line points by finding the mean of each corresponding lane line points on both sides. But we will only find the extrema of the probable road path because that is the only necessary points to compute the complete road path. Let's talk about the start point of the probable road path shown in this yellow color. This is computed by computing the mean from its corresponding lane line points on both sides. And the same can be said for this particular blue dot, that is the end point of the probable road path, and is computed by computing the mean of its corresponding lane line points on both sides. Now, this is the start and the end point of the probable road path. Now, based on these 2 points, we are able to estimate the probable road path shown here in the orange dotted line. Now we have the information to represent the lane's direction. But how do we represent the car's direction? Shown in this red vertical line is the car's direction. And the way to understand this is, if you remember the position of the camera on the car, it was placed right on the top in the center and facing forward, which meant wherever the camera was seeing, it was the car's direction. So this particular red line is actually representing the car's direction. So we have both the lane's direction, the lane start, and the car's direction and the car's start point. Now, based on these 2 information, we are able to compute the error between these 2 values. For example, the distance between the start point of the car and the lane is known as displacement, shown right here. And the angle made between these 2 car and the lane angles is known as the angle, error of the angle. Now, based on these 2 particular errors between the car and the lane, we are able to compute whether and how much error do we need to minimize to keep the car following the lane. Now, to put these things into perspective, we will impose or superimpose these particular detected lane direction and the car's direction on the actual frame they were extracted from. For example, this red line shows that the car is headed on the left-hand side of the road, right somewhere here. And the road direction or the lane's direction is represented in this orange line. Now, to recap this again, we had the lanes combined when combining the MNO, or the mid and the outer lane, into a single frame. Now, based on this information, we were able to extract the detected lane. Now, from the detected lane, we were able to compute the probable road path shown here in the blue line. And the red vertical line actually represented the car's direction. Now, based on these points of information, we are able to compute where the car actually is with respect to the lane lines and where it should have been to follow the road path. So this was the theory behind the data extraction for the lane detection module. And now we will talk about its code flow. Coding for the final section in lane detection, we will be getting the complete lane lines as an input. And we will extract the following output. Number 1, the distance and the curvature, the 2 error values that best relates the car's position to the lane lines. Number 2, the projected lane region to display for our understanding. Hi guys, previously we completed the cleaning stage of the lane detection where we got the lane lines in the best possible place like we wanted. Now in this training session, we are looking to extract the useful information about the road trajectory and the car's direction, also getting the error values that relates these 2 terms. Now for this purpose, I've created a new file that I've named as lane d data extraction.py file. Now this particular file will be used to implement the 4th and the final step of the lane detection module. Now inside it, I've declared the function fetch info and display. Now this particular function takes in 5 arguments of mid lane edge, mid lane, outer lane, frame, and offset correction. Now the very first thing that we need to do or perform in this particular function is to extract the lane trajectory. Now the lane trajectory is simply the path which the car needs to take to successfully follow the lane. Now instead of finding out every point of that lane trajectory, we simply opt to find out the start and the end point of our lane trajectory. Now elaborating over this algorithm that we use to estimate the lane trajectory points is shown on this top window in this particular image. Now here you can see the lane points algorithm, which is used to estimate the start and the end point of our lane trajectory points. Now starting with the top point, to estimate the top point of our lane trajectory, what we simply do is simply use the corresponding mid lane and outer lane top points and average them out to get the top point of our lane trajectory. In the same way, for the bottom point of our lane trajectory, we use the corresponding mid lane and outer lane bottom points and average them out to get the bottom point of our lane trajectory. Once we have the start and the end point of the lane trajectory points, we can simply connect them by drawing a line between these 2 points, which then gives us the estimated lane trajectory. Now this particular path will be an estimate of the actual trajectory, but it will be enough so that the car can actually follow the lane. Now let's implement this function. Now first what we do is simply declare this function or call this function right over here by writing lane points, writing mid lane, give it the outer lane and offset, which gives us the output of trajectory lowest point and the trajectory above point. Now let's define this function. So we define lane points, give it the mid lane, give it the outer lane, and provide it with the offset. And then the very first thing that we do in this particular function is to extract the contours that represents the mid lane and outer lane. And that can be done by simply cv2 find contours. Provided the mid lane, for the mode, we write retrieve external, so simply retrieve the external points And then for the method, simply chain approximation, simple. Then we retrieve the first output of this particular function. These are the contours. What we get as an output is mid contours. The same process will be repeated for the outer contours by simply replacing the mid with the outer. Once we have the outer lane and the outer contours, then we can proceed on to the next step. Now, the next step that we need to do is simply sort these contours out by using a function available in the utilities.py, that is the coordinate sort function. Now let's import that function. That is, from utilities, import coordinate sort. Now this particular function will be used to sort out the coordinates on the basis of rows. Now we call this function of coordinate sort. Oops. Provided the two arguments of mid contours and the order, which is on the basis of rows. So we wanted to sort it on the ascending order on the rows. This gives us mid contours sorted on the basis of rows. So mid contours, row sorted. We do the same for the outer contours and sort them out too. What we get as an output are the outer contours, row sorted. Once we have the outer contours and the mid contours sorted out, the next step is to simply extract the maximum number of contours present in each of the mid and the outer lane. So we want to find out the number that represents the maximum number of contours present in that lane. So that can be done by simply using the shape function. So we provided mid contours row sorted dot shape. We want to access the rows. So how many contours are in the mid contours? So this gives us m rows. We do the same for the outer contours, find out their rows, and save it. Once we know the maximum value or maximum number of contours present in that particular vector, the next thing that's left for us to do is to simply extract the corresponding top and the bottom points of our mid and outer lane. Now let's start with the bottom points. So we write m rows bottom point. So let's save it by simply extracting from the mid contours row sorted. Now the bottom point, the top and bottom point is simply the last point that is present in that particular vector. So that can be accessed by simply writing the index, simply providing it the m rows minus 1. And then for the columns, we simply say get all columns. So we get the bottom point of our m rows. We do the same for the outer contours to get the bottom point, replacing the mid with outer. Oops. And then replacing the m rows with o rows. Now once we have this, we then try to estimate or find out the top point. Now the top point for both the m and the o, let's start with the m. The top point is simply the first point in that particular vector. So what we do is simply replace outer with mid and then replace this with 0. So we access the top point in both these vectors. Once we have the top and the bottom point, all that is left for us to do is to simply use all these corresponding points to estimate the bottom and the top trajectory points as mentioned in the previous algorithm. Now starting with the first trajectory point, that is lane trajectory, or let's write it trajectory bottom point is equal to, simply use, as this is a point, so it's going to be in the form of tuple. So we write this small bracket and then try to estimate the first column of this trajectory point. We provided m, as we are searching for the trajectory bottom point, we provided m rows bottom point, give it the first index, add it to the outer rows bottom point, and then simply divide by 2. Because we have divided by 2, we are doing an average, we need to convert it into int, back to int. Once you have done this, we have now the row or column of that particular point, and now we need to estimate its row. For the row, we simply replace the index with 1. Once we have done this, we now have the trajectory bottom point computed. Now we do the same for the top point. So trajectory top point is estimated in the same way by replacing the m rows bottom with m rows top, outer rows bottom to outer rows top. Now once we have done this and typecast it to int, what we have returned is simply both the points of our lane trajectory. Now we can simply return them as trajectory bottom point and trajectory top point. Now this has been returned. Now we need to also cater for the case whether if either one of those mid lane and outer contours were not present. So what we need to do to cater for this exception, but we simply say that if mid contours and outer contours are present, then do all these operations. Otherwise, simply return 0 and 0 as a dummy trajectory points. And once we have done this, we are done with our first step. So our lane trajectory points has now been estimated, which are the bottom and the top points of our lane trajectory. Now moving on to the next step, which is compute the distance and the curvature from those trajectory points. So now we are trying to estimate the error values by relating the lane trajectory with the car's direction. Now to understand this, let's look at the image once more. Now if you look in the bottom window of this particular image, you will understand how the error values have been computed. Now, understanding this particular image, you will need to understand where the lane trajectory is. Now, the road trajectory or the lane trajectory is in this yellow line which is slanting towards the right. Now, this green line represents where the car is aiming. So the car is right in the center because the camera was mounted on top of the car. Now it's looking straight ahead and the lane trajectory is turning towards the right. Now, to estimate the first error value, what we will do is simply compute the horizontal distance between the car's direction and the road trajectory from its bottom point. So as you can see, right in the bottom, you can see a red line. Now this red line indicates the distance between the start of the car start and the lane trajectory start. Now this will be the distance error value, and for the curvature, we simply compute the curvature or the angle the road trajectory makes from the vertical. Now this particular angle will be positive on the right side, negative on the left. So these are the two error values that relates both the car and the road trajectory. Now once we have these error values, we have now related how much the car needs to turn and in which direction so that it can successfully follow the road. So let's implement this. So implementing this for the perpendicular distance, all we do is simply compute the distance of the trajectory lowest point with the mid lane centered. Now this gives us the distance or the perpendicular distance between the lane central start to the car nose. Now we have the first error, that is the lane center, and for the second error, we will use a function that simply finds the angle the road trajectory makes with the vertical. And that can be done by providing the 4 trajectory points. And this particular function is part of the utilities.py. So we provide it in the form of find lane curvature by importing it. Once we have done that, we can now move on to the next step. Now moving on to the next step, which is simply keep only those edges that are part of the mid lane. Now there can come any error values that might creep up in the mid lane edge. So we want only those mid lane edges that are also part of the mid lane. And then, now that we have extracted the lane trajectory points and the error values, our main concept or main target of extracting the useful information from these lane trajectory and the car's direction has now been completed. We have also extracted the error values that relates these two terms. Only thing left for us to do is to simply display the car's trajectory and the road trajectory so that we can relate them on a more visual base. So for that, what we need to do is simply draw them both mid lane and outer lane on the same matrix. And this is done by simply bitwise OR, where we store them in the lanes combined. Now once we have them in the lanes combined, we want to draw the projected lane or the region in which the car can move. This will be drawn by creating an empty matrix that is projected lane and then finding its contour. Once we have done that, we proceed on to the next step. For the next step, what we simply do is that we fill that projected lane by using the OpenCV function of fill convex poly. Now this particular function, all it does is we provided the contour and it fills that contour with everything that it's got. Once it's filled, we have now the projected region or the region in which the car can move. Now this will be displayed in the green color. Now for the next step, when we draw the projected lane, we will get an error that the mid lane was estimated and it was not the correct mid lane. So we need to get rid of that mid lane, extra values that we have got from the estimation of that mid lane. So to get rid of that error, we need to create a new function that is estimate non-mid mask, which simply estimates the non-mid region from that mid lane. So we estimate it by writing that function on the top here. So we define that particular function of estimating the non-mid mask right here. Now once you have defined this particular function, it simply takes the mid-edge region of interest and then what it gets as an output is a non-mid mask. Now everything except the mid lane. So once we have this, we can use it inside this particular function by multiplying it or bitwise ANDing it with a midless mask with a projected lane. And what we get as an output is simply the region that is free from that mid lane. Now the next thing that we need to do is simply draw the projected lane on that particular lane draw frame. And once we draw that frame, we can now see whether that particular region that we have drawn is the actual region in which the car can move. Proceeding further, we now draw the two things that were the lane trajectory and the car's direction. Now these two things that we mentioned in the first step can now be drawn using the CV2 line command. Now once we have drawn these lines representing the region in which the car can move and where the car is moving, we will also draw the distance between the car start and the lane trajectory start. And this can be done by simply drawing a horizontal line from the lowest most point of our lane trajectory and the car start, which is the image center. Proceeding further, we simply complete this particular function by simply drawing or displaying the distance and the curvature value that we have just extracted in the second step. Now these two error values were relating our car's direction with the lane trajectory. Now these two error values will primarily help us in estimating how much the car needs to move and in which direction so that it can successfully follow the lane. Now once we have completed this, we can now proceed on to calling this function in the lane detection module. Now let's do that. Now moving back to the lane detection module, we simply add in, after the extend short lane, that was the third step of the cleaning stage, we can now add in our fetch info and display. Now that is imported from the data extraction and then we declare it right here. We provided the inputs of mid lane edge, extended mid lane, extended outer lane, image crop, and offset correction. Once we have provided these values, what we get as an output is the distance and the curvature, the two error values that relate the lane trajectory and the car's direction. So now we have completed our lane detection module. Now let's see how it works out or it pans out when we run this particular project at this location. So for that, we move to a terminal, build our system by Qualcomm build. Once we have built it, we launch our simulation. And once the simulation has been launched, we now launch the computer vision node. Once we start the computer vision node, you will see the final output. As you can see, all the rest of the outputs are displayed previously, but on the frame, you can clearly see that everything has been displayed so that you can see that the lane detection module has been successfully completed. This green region represents the region in which the car can move in any direction. Apart from this blue line represents the road trajectory which the car needs to take so that it can successfully follow the road. And this red vertical line represents where the car is headed at this particular moment. And this blue horizontal line simply displays the distance between our car start and the lane trajectory start. This is the first error value, and this is in values of pixels, that is 11. Because the lane trajectory is on the right hand side, it has a positive of 11 pixels. And for the curvature, what we have is simply displaying the angle the lane trajectory is making from the vertical. At the moment, it's only this 2.5 degrees towards the right. And this is positive because it's turning positively towards the right. Now, if it was of any more than this value, then the car would need to make a very sharp turn, which it will once the car reaches that particular turn up ahead. At this moment, we have extracted the useful information from our road, and we can now leverage this information and create our control module, which will make the car move or follow this particular lane and complete the lane assist feature as a result. So till then, thank you and bye. So we have extracted reasonable information from the lane lines, and now we will utilize it to reduce the steering parameters required to keep the car following the lane. This means that we are ready to define our first rule-based control algorithm named after the feature follow lane. Before looking for a solution, let's analyze our information, the problem that we have at hand, and what are the constraints that we might face in solving for that problem. The information that we have extracted after lane detection are the two error values. Number one, the distance, and number two, the curvature, and the projected lane region. The problem or the feature that we might want to develop is that we want our car to follow the lane. And the constraint or the issues that we might need to navigate around while developing an algorithm are as follows. Number one, the max angle the road will turn on both sides. Number two, the max angle the car can turn on both sides. And number three, the issue of car overshooting in turns at high speeds. For coding, we have the information provided by the detection algorithm right here. And we'll be computing the two control parameters, the angle and the speed, that will help the car navigate the lanes. Hello guys. In the previous coding session, we finally completed the detection stage of the lane assist feature. This means that we are ready to define or estimate the control parameters from the extracted information, consequently providing our self-driving car with the crucial ability to follow lane. For this purpose, we move inside the drivebot.py and define a new class that we name as control. Now, this particular class that is named as control will house every control system related to any feature that we wish to develop for our self-driving car. For example, at the moment we are defining the lane assist feature, and the control system of that lane assist feature that will be defined as a function inside this class. Let's name it as follow lane. It takes in three arguments of max lane distance, and curvature. Now, the last two arguments are simply the two error values that we receive from the detection stage in the lane assist feature. Now, defining this particular function or the control system for our lane assist feature, the very first thing that we need to do is simply define three constants that will be used in this particular function. Those are the max turn angle. This is the maximum turn angle that can be achieved by the lanes on the road. That is 90 degrees to the right. Now, in the same way, the max turn angle in the negative direction will be negative 90. And for the third constant, there is required turn angle. Now, this particular variable will be used and initialized to 0 and used to estimate the required turn angle by the car to follow the lane. Now, let's move on to implementing the first step of this particular function. Now, if you remember the algorithm defining the theory for this particular control system, we defined that we need to estimate or calculate the required turn angle that the car needs to take from the given error terms. These were distance and curvature. We start off by using or testing the distance term by comparing it with the maximum allowed distance or the maximum sane distance. So what we write is that if distance is exceeding the max sane distance, or it is exceeding the max sane distance in the negative side, then this is basically signaling an out of bound condition. So this is not a normal condition. So we need to cater for what will be the required turn angle for this particular condition. Now, we first define the first condition inside these two conditions. That is, if distance exceeds in the right-hand side, the distance is greater than the max sane distance, then we simply compute the required turn angle as the max turn angle added to the curvature. So basically, we simply ignore the distance function or distance variable and simply replace it with the maximum angle or maximum turn that the car can take. And we add it with the curvature or the angle the car is taking with respect to the trajectory, which this gives us the required turn angle by the car. We cater for the next case or the other case by simply writing required turn angle is added to max turn angle in the negative direction to the curvature. Now, if the condition is not out of bounds, it is the normal condition, we now can use the distance term or the distance error term that will be used in a way to compute the car offset. Now, the car offset will be computed using an interp function that is part of the NumPy library. So let's import it. From NumPy, import interp. Once we have imported it, we interpolate our distance variable, provided the range of this distance variable, which if you remember, is basically negative max change distance to positive max change distance. And we want you to interpolate or change it to the range of negative max turn angle to positive max turn angle. So this gives us the car offset. Once we have the car offset, we can now compute the required turn angle for the normal condition, which is simply adding this car offset to the curvature. Now, once we have catered for both of these outer bound and normal condition, we can now move on to the step 2 of this algorithm. Now, if you remember, the step 2 was about handling the overflow. So let's slide handle overflow. Now, what we have computed so far is the required turn angle the car needs to take to follow the lane. Now, this angle can, of course, move above than the maximum turn angle that the car or the lane can take. So we need to handle for that overflow. So what we simply write is if the required turn angle that we just computed is greater than the max turn angle that is allowed, or it is less than, the required turn angle is less than the max turn angle in the negative direction, then this is an overflow condition. So we handle for the first overflow condition, that is required turn angle is greater than the max turn angle. Then what we simply do is set the required turn angle to the max turn angle, because there's a maximum angle the lane can turn. We handle for the other case by simply setting the required turn angle to the max turn angle in the negative case. Now, once we have implemented the step 2, we can now move to the step 3 of this algorithm. Now, if you remember, the step 3 involved handling the maximum turn capability of the car. Now, at the moment, whatever turn angle that we have computed, or the required turn angle that we have computed, is the turn the lane is taking. This has a range of negative 90 to positive 90 degrees, but our car can only turn from a negative 45 to positive 45 degrees. So we need to interpolate from given range to the required range. So let's do that. So we write handle max car turn ability. So let's do that. We use the function of interp once more, provided the required turn angle, provided the current range, that is max turn angle negative to the max turn angle positive, and we want it to go to negative 45 to 45 degrees. So negative 90 to positive 90 degrees, we want it to interpolate to negative 45 to positive 45 degree range. Once we have this, we have now handled the max turn capability of the car. Now, we wanted to save it to not the required turn angle variable, but now to the final self.angle. Now, this is a class variable, but we have not declared the class variable as of yet. So let's declare that. We move inside the control class, define the init function. It takes in the argument of self, and then we can define the class variables. That first class variable that I defined is a self.angle. I set it to 0.0, so it's basically a float type. And we also define the other class variable, that is speed. We set it to 80. Now, these two variables can be accessed throughout the class from any member function. At the moment, they cannot be accessed by this particular function unless we define the self as the first argument. And once I do that, the error goes away. Now, whatever interpolation that is being done to handle the max car turn ability, that is being saved inside the self.angle. So angle has been updated according to the lane conditions. Now, this means that the follow lane function or the control system has been completed for the lane assist feature. Now, all we need to do is create a particular function inside this controls class that will call all of the different systems, all of the different control systems through a central hub. So let's create that. Inside this particular function, inside this particular class, we create a new function that is define drive. Now, this takes in argument of current state. Now, this particular function will be called from outside or from other class, that is the car class. Now, this particular function will take in the current state of the car as its argument. Now, we provide in the current state to it, which will basically be, at this moment, if we unpack it, the distance, the curvature, and the image. So once we have this unpacked from the current state, we can move on to the next step. Once we have unpacked all the values that we might get from the main car class, we can then move on to the next step, that is check if the distance is the same value. So if distance that we have got from the previous stage is not equal to 1000, that was an unknown value, the same way, and curvature is not equal to 1000, and this indicates that we have found or detected a lane, then we can actually call that particular function from our control class from same class. Now, let's call that function. So that is self. So at the moment, we need to define the self for this drive class. Once we do that, we can now access our follow lane function. We provided the max change distance, which will be simply the maximum allowed distance that can be simply max image.shape, or basically columns divided by 4. So quarter of a column is representing the maximum allowed distance for which the car can go from its center. That will be the first argument, and the next two arguments are very simple: distance and curvature, the two error values that we got previously. Once we have this, we have completed the self.follow lane function and called it from the drive or the main central hub inside the controls class. Now, we need to cater for the other case where if distance and curvature are not correct values. For that particular case, we need to set our self.speed back to 0. So we need to basically stop the car if the lane detection has stopped. Otherwise, normally in the follow lane, we want to reinitialize the speed of the car back to 80. Now this is done, reinitializing of this particular speed is done because the self.speed will be modified multiple times in this particular case for displaying it. Now, at the moment, it's not been modified, but later you will see that it does get modified. For example, right here, once we have this self.speed, which is set to 0.0, once we set this self.speed or self.angle, we both interpolate it to the values which the car can take or the motors can take that is defined inside the car. So let's do that. So we use the interp function once more inside the drive command. We tell it to take the self.angle provided the range that this self.angle is taking, that is -45 to +45. It will be modified now to 0.5 to -0.5. Now this is the range the motors can take for this to achieve this particular angle. So in the real world, they're achieving -45 to +45 degrees, but we need to pass in +0.5 to -0.5 values. So this gives us the self.angle back. So basically, we are transferring or interpolating angle and speed from real world to motor world. Let's replace with this dot with comma, and the error goes away. In the same way, we need to cater for the speed, but for the speed, we need to also say or set the self.speed by using the interp function once more, provided the self.speed as argument, provided its range, that is 30 to 90, and the values that the motor takes for this speed command is simply 1, 1 to 2. So once we have given this, our self.angle and self.speed are basically completed. Now, basically, our main drive hub inside the control system is now completed, and we can call it inside the car class. So how can we access a different class from our car class, that is the controls class? To access it, we need to first define the object or instantiate that particular class object inside this car class. So we need to define an init function for this car class that will basically initialize its member variable that we name as control, and it call in the object of the control class. And once we have this, we now have access to the control class and its member variables and member functions. Now once we have that, all we do after the detection module, we save the distance and the curvature inside the current state. So let's write here current state, make it a list, pass in the distance, pass in the curvature, pass in the image. This will be our display image. As you can see, distance, curvature, and image are being passed. And then once we have passed this, we can now call the self.control. Now you can call in the drive function. Now this drive or the main hub of the control system or the control class can now be called. It takes in the input argument of current state. And once we have called this, it basically calls or passes in this current state. This current state goes inside the drive function, which is the main hub of the control class, which basically extracts it or unpacks it, the distance, curvature, and the image, and then using that image to define the maximum distance, and the curvature to the follow lane function. If the distance and curvature were same values, then the follow lane function estimates the required turn angle and updates the self.angle. And for the self.speed, it is basically initialized to 80. Otherwise, if the given error values were incorrect, representing a misdetection of the lane, then the self.speed is simply set to 0 to stop the car. And then once you have the angle and the speed, we simply interpolate them from the real world values to the motor values, which the motor needs to be set at to achieve those real world values. So once you have done that, we have the self.angle and self.speed updated to follow the lane. Now all we need to do is simply return the two member variables of the control class. So let's do that. So the first is self.control.angle, and the second is self.control.speed. Once we have returned this, we move inside our computer vision node. Here, instead of initializing angle and speed to 0 and 0, we comment this out, retrieve the angle from the drive car function. Then we retrieve the speed from the drive car function. Oops. And then simply update the velocity angular z to angle and linear x to speed. And once you've done that, our system or control system of our lane assist feature has been completed. Now one more thing that I want to add just for visualization purposes is the display function. So let's do that inside the drivebot.py. So we define that function, that is the display function, right here. This particular function simply displays the state of the control system for each feature that we define. We pass in the frame display angle of car and the current speed, and it displays it on the screen. Now let's call it after the self-control.drive after we pass in the current state, which basically updates the angle and speed of the car. So we call it after we have called the self-control.drive function. Right here, self.displayState, which basically takes in the image, the control and speed variables of the control class. So this is control class. Once we have done this, our control system or the lane assist feature has been completed. So all that is left for us to do is simply build this module and see for ourselves whether the car was able to successfully follow the lane. So we move inside the terminal. Right here, Qualcomm build, launch the simulation. Once the simulation starts, we can run the computer vision node, and the car starts to move. And you can see what the lanes have been found, the curvature and distance have been computed, and the car starts to turn from that lane. And once it makes the turn, it then goes back straight. So as you can see, the car has made that turn very smoothly, I might say, and we have successfully completed our lane assist feature. So as we have defined the very first feature for our particular car, we can move on to define the second feature for our self-driving car, that is cruise control. Till then, thank you and bye. Moving on to the second most important feature of any self-driving car, that is to obey the road speed limits. The self-driving car is required to gather or detect information about the speed signs on the side of the road. This information will be extracted in 3 stages. Number 1, localization. Number 2, classification. And number 3, cracking. Once we have gathered sufficient information, we can then move on to developing the control algorithm that will adjust the speed of the car to comply with the local speed limits. If we want our car to always obey area speed limits, it needs to detect and understand each speed sign on the road. This means that we are primarily concerned with these 3 things. Number 1, we want our car to localize any sign that is in front of it. Number 2, we want to understand what that sign means. And number 3, we want to keep track of its location until it is no longer available. Something like this. The signs that our car will be able to detect and act upon are the 4 speed signs, 30, 60, 90, and stop, and the left turn. In the case of signs, means to localize the signs in every frame. And then classification is performed on these localized signs to identify what that sign was. For example, in this case, it was a speed sign 60. Hello guys, so we were talking about the localization stage in the sign detection module, and we just went over the first approach of detecting the circles in an image. And now let's talk about the second approach, that is using the huff circles to detect those circles. Now the huff circles method is a method similar to the huff lines process that we studied in the earlier stages of the course. But instead of detecting the lines in an image, this method is used to detect the circles. Now to understand this concept a little bit better, we first need to do a quick recap of the huff lines process. If you remember, any line can be represented in the form of slope, intercept form, and a parametric form. In both of these forms, the line is represented by just 2 parameters. To understand the huff lines process, let's look at this image here. Here, 2 points in the xy domain will be represented in the parametric or the huff space of the rho theta domain. Now here the points are represented in the huff space in the form of curves. And where these curves overlap, or the maximum overlap point, will be the point that represents the line made by those 2 points in the xy domain. So this means we would require an accumulator behind the huff space to count the area of the maximum overlap. This means that accumulator would have the same number as the same number of parameters in this initial equation. So we would require a 2D accumulator to detect the lines in an image. Similarly, to detect or determine what kind of an accumulator we would require for a circle, we first need to analyze its equation, which is simply x squared plus y squared is equal to r squared. Now here, there are 3 parameters to represent any circle. This means to detect the circles in an image, we would require a 3D accumulator. And naturally, going from 2D to 3D means that we would require manifolds the computation power, and processing power is a luxury that we do not have at our disposal. So instead, what the OpenCV suggests is using the huff gradient method to detect the circles in an image. Now this particular method is a very complex method of detecting the circles in an image, and what the OpenCV tells us about this method is that it uses the gradient information of edges to detect the circles. This simply means that it uses the directional information of edges to detect the edges or detect the circles in an image. And the function that implements this particular method is the huff circles method. And its parameters are, the first is the grayscale image from which we want to detect those circles. The second is the method that we just discussed, the huff gradient method. The third is the unit of the Hopf space, naturally is set to 1. 4 is the minimum distance between two circles to be considered as separate circles. Then we have the parameter 1, which is simply the high threshold of the Canny edge detection algorithm. 5th is the parameter 2, or the minimum votes required for any circle to be considered as valid. And then we have the minimum and maximum radius, or the radius range for any circle to be considered as valid or useful circle. So this was the theory behind the Hopf circle method of determining the circles in an image. Now let's talk about this code flow. Coding the localization stage requires the original frame extracted from the video as an input. And we want to localize any circular regions that may exist in our frame using Hopf circles. These will probably be our signs. Navigation. Now both of these abilities requires the information to be extracted from the traffic sign besides the road. So in this coding session, we'll start or solve for the first stage of sign detection, that is localization of signs. Now for this purpose, we move inside the detection folder. We have created a new folder that is signs, and inside it, we have found a new script that is sign detection.py. Now this particular script will implement the sign detection module inside of it. Now inside, we have declared the function that is detect signs, which basically takes in two arguments of frame and frame draw. Now the first argument of frame is the original frame in which we want to detect the signs that are present on the road. When the second argument will be used to display those detected signs to the user. Now, solving for this particular function or defining it, the very first step that we need to do is convert that PGR color space frame into grayscale. And that can be done by CV2 convert color and providing it the frame as a source and the color space conversion as the BGR to gray. This gives us the grayscale image as an output. Once we have this, we can now call or define our next function that will actually implement the localization of signs. Now, if you remember, all our signs that are present inside the simulation have circular shapes. So we can leverage that feature and simply try to localize all the circular shapes in our simulation. And that can be done by the OpenCV function Hopf circles. So let's define a function that actually implements all the detection and the tracking inside of it. So let's define sign detection and track function. It takes in three arguments. First is the grayscale that will become the input of the Hopf circles function. Second is the frame, and third is simply the frame draw. And these three arguments will become the inputs of this particular function. Now for the very first step, that what we need to do is simply perform the localization using the Hopf circles function. Now if you remember, the Hopf circles takes in the first argument, that is the image, as the grayscale. So we provided the grayscale that we have converted earlier. Let's provide it the gray as the input. The next is the method which the Hopf circles will use to detect or localize the circular shapes. That is Hopf gradient. And the third argument is the DP, or simply the resolution of the Hopf space. Now we will set it to 1 so that the resolution is same as the resolution of the original image. Then we move on to the fourth argument, that is the minimum distance. Now the minimum distance is simply telling us or providing us that the minimum distance between the circles to be considered as a valid circle. Anything that is less than that the minimum distance, that circle will be considered as the same circle and simply discarded. So we set this to a high value because most signs are not close to each other. So let's suppose we write here 100. Then we move on to parameter 1 as the fifth argument. Now the parameter 1 is simply the high threshold value of the Canny edge detection algorithm. Now the Hopf circles function also performs edge detection as a preliminary step inside of it. So this requires the parameter 1, which is basically the high threshold value for the Canny edge detection algorithm. We provide it 250 as its value. Then we move on to the parameter 2, which is basically the value or number of votes that a circle is considered to be a valid circle. So basically, how strong you consider how strong you consider a circle to be a valid circle. So we provided a good enough value, that is 100 again. Then we provided the minimum radius as its sixth argument. Now the minimum radius is basically the radius range. The minimum and the maximum radius is basically the radius range for the circles to be considered as the valid circles by this Hopf circles function. So we provided a reasonable value of 10 pixels. Then we move on to maximum radius, and then we provided 100 pixels as the maximum because we considered these range to be an adequate range for detection of signs that are of circular shapes. Once we provide all the arguments, what we get as an output are the circles. Now once we have these circles localized by the Hopf circles function, we move on to implementing the next step. For the next step, we simply check if any circular regions were localized or not. Now, if the circular regions were localized, we simply convert them to unsigned integer 16. Then we move on to the next step, that is looping over each localized circle and extracting its center and radius. Now, this center and radius will be used to extract that particular region so that we can display to the user or train later on. Moving further, we extract the region of interest from those localized circles. Now, whatever circles that have been localized, they are passed through a try-catch block, which basically just extracts those circles by simply cropping them out and displaying to the user as localized signs. Also, displaying circles around those detected circles in the original frame draw. Now, once we have done this, we can simply display that detected signs image. Now, once we have displayed those images, our function of sign detection and tracking first stage, that is localization stage, is now completed. Now, we can simply call this function inside the detect signs function. After we have converted to grayscale, we call this detect or sign detection and track function, provided the gray, provided the frame, and provided the frame draw as the input. Once we have done this, our sign detection and tracking has been called successfully. Now, all we need to do is simply call this sign from the main function or main file of drivebot.py. Now, inside the drivebot.py, after we have detected the lanes or information from those lane lines, we need to call this detect signs function. So first we imported right here, as we have imported from detection signs, sign detection, we import the function of detect signs. We call it after the detect lanes function. Now let's call it detect signs, provided the two input arguments of image and image draw. Now for the image draw, we will provide it image original for the image, because the original image has been modified by the detect signs function, and it has drawn the lanes that have been detected. So what we do is simply create a new matrix that simply copies that original image before it has been modified by the detect lanes function. We provide it to our detect signs function, the original image, and provide the real image, the previous image that has been drawn lane on as the frame to be drawn. So every sign that will be detected will be drawn on the image and then displayed to the user in the computer vision node. Once you have done that, you will see any sign that has been detected as a successfully detected sign, or any circle that has been localized using hub circles. Now let's do that. Now for this purpose, we first need to display this particular sign folder inside detection folder by creating a new file that is init.py. Now, as we mentioned previously, any new folder or any new package to be discovered as a package requires this init.py inside of it. So we define this init.py, and then we move inside the setup.py, and then define this signs module as detection s module, provided its location, which is almost similar to the lane detection folder. Just the difference here is that instead of lanes, we provide signs. Then we simply copy this over to the packages and then mention this package of sign detection folder. Once we have done this, we can now build this particular module and see the results. Let's try to build this. Once it has been built successfully, we can launch our simulation and see what happens. Now, at the moment, the car is standing on a turn and it is approaching a sign right there. Now, if I run the computer vision node, let's see the results. So the car starts to move, and let's see what happens. So it's following the lane, which is the lane assist feature, which was working successfully when we finished it last time. So whenever it approaches its first sign, you will see whether it detects it or not. So at the moment, it just missed it. Maybe the threshold is set too high. So we need to lower the threshold so that it can be detected in this case. Now we set the threshold that is parameter 2, change it to 100, from 100 to 30. We lower that maximum vote, or the votes that is required for any circle to be considered as valid, down from 100 to 30. Now let's see the results once more. We build it again, launch the simulation again, and run the computer vision node. And the car starts to move again. And as you can see, the lane assist feature seems to be moving quite well. So moving further, you will notice that the sign detection algorithm will also run its best once it approaches a sign. Now, as you can see, here the signs have been localized, and this is the region of interest that has been displayed to you. Now, as you can see, this localization using the hub circles is working perfectly for the circular signs that we have put up inside the simulation. And this was bound to work perfectly because this circle or this function works very best for localizing circular regions in the image. And that is the primary purpose of this function. And this was what was required for localizing signs in our case. Now, we can move on to the next step, that is classifying these signs as whether these localized circular regions are actually signs or not. And that can be done using the CNN, or convolutional neural network approach. Till then, thank you and bye. Hello guys, implementing the localization stage not only provided us with those localized signs, but also gave us the data that was required to train the classification algorithm. Some of those examples from that training data is shown right here. As you can see that there are a lot of signs being detected along with a lot of other things. The two targets that we want to achieve in the classification algorithm is shown here. First is that we want to separate out the signs from everything else. This is known as a binary classification problem. Once we have separated out the signs from everything else, we are ready to categorize those signs into separate categories. This is known as a multi-class classification problem. For example, we want to create a separate class for speed sign 70 and a separate class for speed sign 80. So these are the two targets that we want to achieve in the classification algorithm. Now let's talk about the probable solutions to this problem. The first solution that comes into my mind is known as CNN. Now what CNN means is a convolutional neural network. Now convolutional neural network are two terms. First is convolutional, second is neural network. Let's talk about the neural networks first. Neural networks are useful function approximation algorithms that mimics the activity of a brain. Function approximation algorithms are those algorithms that try to approximate a function given a specific data. This is the same process that is followed by a brain. For example, when you show several times a cat to a kid and tell it that it was a cat, the next time that it sees a cat, it will understand that that was a cat. So what the brain was doing, it was understanding what features make up a cat. So the same procedure is followed by the neural network, where it will understand what features make up a specific object. So the simplest neural network is also known as a perceptron. This is composed of a single neuron. Its working is as follows. The input is being provided to that perceptron, and then it is get multiplied with a weight and then added to a bias. Then a nonlinear activation function is being multiplied to that data to give us our desired output. So the question arises, why was a nonlinear activation function being multiplied to that data? The reason is that most of the data in the real world is nonlinear in nature. So to approximate that nonlinear data, we require a nonlinear function approximation algorithm. So this was the forward pass of a single neural network. Now let's move to the convolutional neural network. So CNNs, or convolutional neural networks, are deep neural networks that have two layers that are specific to them alone. So what is a deep neural network? If you remember the structure of a neural network, it has input at the start and output at the end, and in between lie a hidden layer. Now if these hidden layers are more than one in number, then that is probably a deep neural network. So CNN are those neural networks that has more than one hidden layer, but they also have two layers that are specific to them alone. Those are convolutional layer and max pooling layer. Now let us try to understand the CNN layers. We will start off with the layers that are specific to CNN alone. So convolutional layer is the key layer that provides CNN the ability to mimic image processing abilities. If you remember, in image processing, we used to extract certain feature by convolving a kernel over the whole image. The same process is followed in the convolution layer, where a kernel is being convolved over the whole image to provide a certain feature. This process is known as convolution, and it is being shown in this GIF image right here. And as you can see, the yellow color kernel is being convolved over the green color image, thus providing us with this pink color convolved feature as an output. Now, if the same procedure is being followed in the convolutional layer and image processing feature extraction, so where is the difference? The difference lies in the way we extract or we set the kernel weights. In the image processing, we used to set these kernel weights manually, but in the CNN, these weights are set automatically by a function known as backprop. This provides the crucial ability to CNN to detect a certain object because the convolutional layer is only extracting those features that best defines those objects. So this was the convolution layer. Next is the max pooling layer. In the max pooling layer, we extract only the most relevant portion of information in the image. It does so by working in batches, and which means that the image is further subdivided into smaller subwindows. For example, in this pick subwindow, you can see that the highest value is 20 right here. And this 20 value is the area of the highest response, and it will be the only value being extracted after applying the max pooling layer. So this provides the crucial ability of robustness to CNN. What this means is that irrespective of the location of the object in the image, that object will be detected by the CNN after applying the max pooling layer, because that area will be the area of the highest response, and max pooling layer will be able to sort that area out. Next three layers are not specific to CNN alone. For example, the dropout layer randomly drops the input unit to 0. An example of this can be seen in this image right here. As you can see, in the hidden layer, the second and the fourth neuron has been set to 0. Because we have less neurons to worry about, this provides or reduces the complexity of the network, and in turn provides more generality as a whole. This also prevents overfitting over the data. For example, if we have a simple data and a very complex network, then that complex network will try to memorize that data instead of trying to approximate a function that best describes that data. So instead of changing the architecture of the model, the dropout layer provides us with that ability to simply drop certain neurons to simplify our model and just providing a general solution over that data. Next is the flattened layer. Now, flattened layer performs a simple function of converting n-dimensional data, for example, as shown in this image, to a single-dimensional vector. It does so by converting or dividing the window into smaller sub-windows, and then in each sub-window is turned to a vector which is stacked on top of each other with all other vectors. This provides us with a single largest 1D vector as an output. Last but not the least is the dense layer. In the dense layer, we have multiple neurons instead of a single neuron, and because we have multiple neurons, the kernel is a matrix and bias is now a vector. But the procedure for extracting the output remains the same. For example, the input is being multiplied with the kernel matrix and being added to the vector bias. And then a nonlinear activation function is being applied to the product, and thus we get the final output. So this was the theory behind the CNN layers, and now we are actually ready to build our own custom CNN model. Alright guys, it's time we implement our own custom CNN model. The library that we are going to use is known as Keras library, and there are multiple functions available to implement each layer of the CNN architecture, and let's study them one by one. Starting with the convolution layer, the function available to us is known as conv2d. Its first argument is known as filters argument, which describes the number of filters for that particular kernel in this conv layer. For example, in this image, you can see that there are 3 filters being used for this particular kernel. Next comes the kernel size. Now, kernel size describes the size of the kernel, and it is always going to be square in its nature. So its kernel size will always be n cross n. Next comes the argument of activation, or a nonlinear activation function will be provided by the user, and it will be acted when the convolution has been performed between the kernel and the image, and which gives us the convolved feature as the final output. The final argument is the input shape, and it's just image height, image width, and the image channels. Now, this information about the image or the input was necessary because the kernel needs to know how many strides it needs to take to perform the whole steps of convolution. To implement the max pooling layer, we have a function known as max pooling 2D. It's the only argument that we are worried about, or it is important to us, is known as pool size. Now, pool size simply describes the size of the sub-window that we want to take when extracting the area of the highest response. For example, right here, the pool size is 2 cross 2. Now here what you will notice is that the pool size filter is also square in its nature. Now to implement the dropout, the function available to us is dropout and its argument is rate. Now to understand rate, let's look at this example. As you can see, the second and the fourth neuron in the second layer of the dense network has been dropped out. So the dropout rate right here is 0.5 or 50%. Next, the final layer of the CNN network is known as dense layer, and it will be implemented by the function known as dense. Its first argument is known as units, or the number of neurons. For example, if we want to add this particular dense layer to this network, all we need to do is set the dense layer's number of units or neurons to 3, and set the second argument as the activation that we want to provide to this dense layer. So these were the functions that will be used to implement our own custom CNN architecture. Now let's implement our own CNN. So in coding, we'll first build a CNN model, preferably 2 hidden layers, that will take in the localized circular region from the previous localization stage as an input. And then the CNN model will try to make sense of what that sign was, if it was a sign at all. For example, in this case, we had one localized circular region, and it was correctly classified as a speed sign 60. Okay guys, it's time we build our custom CNN model. So we start out by setting the model to sequential, which simply means that the input is being provided at one side and the data moves from each of the layers, and then we get the output on the other side. So the data was moving in a sequence, and this is why it's known as a sequential model. The first layer that we add to this model is known as conv2d. To understand why we added this layer, we need to go to the points of theory that mention that the convolution layer and the max pooling layer were the primary building blocks of a convolution neural network. We set the filters to 16 and the kernel size to 3, and 3 kernel size is the default kernel size for conv2d layer. Then we set the activation function to ReLU, and to understand why we set ReLU as the activation function, we need to look at its graph. Right here, you will see the function that defines the ReLU activation function. And as you can see, the output is equal to max, 0, and input. This simply means that the negative input will be turned to 0, and positive input will be set to as it is. So why do we need such an activation function? The ReLU activation function is used to tackle a problem known as vanishing gradients. To understand the vanishing gradient problem, you first need to understand the structure of a deep neural network. As we tend to go deeper and deeper into a deep neural network, we add an activation function at each of those layers. Mostly those activation functions were the sigmoid activation functions. And what sigmoid activation function does is, as input tends to become larger or smaller at either sides, the data is being squashed down to 0 and 1. So the range of a sigmoid activation function output is 0 and 1. So going from a very large range value, we tend to go to a very small packed range values. And when performing the backprop on this sigmoid activation function, where we are trying to learn the weights of the kernels of the CNN network, then we need to perform the gradient of this sigmoid activation function. And this gradient turns out to be something like this. So as you can see, at the extreme, this gradient or this derivative tends to become 0, or this gradient is vanishing. And the problem this vanishing gradient poses is that the network is no longer to train as the gradient has become 0. So to tackle this problem, we use the ReLU activation function instead of the sigmoid activation function. Moving back to our CNN model, we set the input shape to image height, image width, and the image channels. Then we add in the max pool 2D, the second crucial layer of the CNN network, and set the pool size to 2 and 2. Then we add a dropout layer for better generality over the data, and we set the rate to 0.25 or 25%. Then we are going to add the second convolution layer. So if we already have first convolution layer, why do we need to add another convolution layer? To understand this, we first need to understand what are the features the first convolution layer was extracting. The first convolution layer was extracting only the simpler features, such as the edges or the corners that define that object. As you tend to extract or use more and more convolution layers, they tend to extract more and more complex features. So the more convolution layer you add into a network, the more accurate that network will be in predicting that particular object, as you tend to extract more complex features. So we are going to add another convolution layer right here, and we start off with a conv2d layer. But this time the filters are double in number than the previous layer. This is 32 to the 16 that we used previously. So as you mentioned, the next convolution layer will always extract more complex features than the before layer. So this is why, and these complex features tend to define that particular object more than simpler features that we extracted before. So this is why these features are more important to us, and we will extract more number of features in these subsequent layers. The kernel size and the activation function will be the same as before for the reasons mentioned before. Then we add in the max pool 2D and the dropout with the same arguments as we did for the first convolution layer. Then we add the function known as flatten, which flattens the n-dimensional data down to a single dimensional vector, which will become as the input of the fully connected network and the next layers. Next, we add in the fully connected network that will be used to categorize into different classes. First will be the first dense layer that we are going to use and set the units to 32 or 32 neurons, and the activation will be ReLU for the same reason that we mentioned before. Then for the final layer, the number of units will be the same as the number of classes, as this layer will be performing the categorization or the classification into multi-class. And the activation this time will be softmax activation. So why did we use softmax instead of ReLU that we were using previously? To understand this, Let's look at the graph of a softmax activation function. Right here, you will observe as the input values tend to become larger in the positive side, the softmax tend to become 1. And the range of a softmax activation function is 0 and 1. But this range of an activation function was the same range as we studied for a sigmoid activation function. So why did we use softmax instead of a sigmoid activation function to perform the multi-class classification? The answer lies in the way or the probability the probabilities are related to each other in the softmax activation function. In the softmax activation function, the probabilities, for example, for a 3-class classification network, the probabilities are related to each other in such a way that if a network is predicting a 3-class classification probabilities, then the probability of 0 added to a probability of 1 added to a probability of 2 will always be equal to 1. So all these probabilities will always be equal to 1 as they are interrelated to each other, and they tend to add up to 1 probability, that is the maximum probability. So this means some point in these probabilities will be the highest point, and that point is the class predicted by that particular network for that object. So this is why softmax is preferred for a multi-class classification over a sigmoid activation function. So we have built our model, and now let's try to visualize our model. For this, I mentioned 2 libraries that are very useful in visualizing deep neural network models. Starting with the Neutron library, you can clearly see the sequential nature of our model. The input is being provided at one side, and the output is being entered from the other side. And in between lie the layers, starting with the first convolution layer, that is conv2D, max pooling, and the dropout. Then we add in the next convolution layer, that is the second conv2D, second max pooling, and the second dropout. The difference lies in the second conv2D filters, which were double in number than the previously. Then we add in a flattened layer that simply converts n-dimensional data to a single dimensional vector. This was crucial as this becomes the input for the fully connected layer or network that will come in the next way. In this fully connected network, the last dense layer will have the same number of neurons as the number of classes. For example, we have a 4-class classification network, so this is why the last layer will have 4 number of neurons. In the same way, visualize Keras helps us in visualizing the same model, but this time we will get a 3D view of the same network. And as you can see, the first convolution layer size is larger than the second convolution layer, but is thinner than the second convolution layer. And the max pooling and the dropout in the same layers are of the same size as the dropout is acting on the layer before it. And right here, you will observe that the flatten has flattened out the data into a single dimensional vector, and it's very long. Next, in the last 2 layers are the fully connected network that is actually performing the categorization into different classes. And we have built a 4-class classification network, so this is why it's giving us 4 classes or 4 neurons in the last layer. Now let's try to train our model on the data that we have. To train our model, we need to first define 2 things, that is loss and optimizer, that we want to train on. This is mentioned inside the model.compile function, where we describe the loss as categorical cross entropy and the optimizer as Adam for a multi-class classification problem. The next we need to define on what metrics do we want our optimizer to optimize our network on. The metrics that I've said is the accuracy metrics. So this particular network will be optimized on the basis of its accuracy, and when we will get the maximum accuracy, the training will stop. To train the model, we use the function known as model.fit, and we provide in the x input, the y labels, for the validation data, we provide in the validation input and the validation labels. And for the epochs, we provide in how many epochs do we want the training to run for. And then we perform our training. This is a snapshot of the training that I've done previously, and as you can see, the training accuracy goes from 98% to 99% in the last 5 epochs. And the validation accuracy is also around 99%. Now that we have trained our model on our training data, we are ready to evaluate on our test set. To perform the model evaluation, the function available in Keras is known as model.evaluate, and we provided the data that is x-test and the y-test, and this gives an accuracy of around 99.66%. So now we are sure that our network is not only performing on the seen data, but it's also giving good results on the unseen data. So we are ready to save our model for future use. This is done through a function known as model.save, and we provide in the directory we want to save into and the extension we want to save into. The extension in the Keras is known as .h5 extension, and our model is now saved, and we can use it in our sign detection module for the detection or the classification of each of the signs in our case. Now let's try to detect or test this out in real terms. Previously, we designed our CNN model. In this session, we are going to train and evaluate our model on the dataset that we have extracted earlier. Now, all the script required are already placed inside the CNN folder inside the sign detection module. We start off by running the train or evaluate script, where we have 2 control variables. These are train and evaluate, as we want to do both, so we set them both to true. And then run the script. What it basically does is extract the dataset present inside the data/dataset folder. This contains the sorted dataset that we have done previously. Once I close this window, it uses the dataset to train the model for 30 epochs. Once trained, it evaluates that model for 6 test images. These images will be unknown to the model that we have trained previously. And as you can see, once trained, it achieves an accuracy of 95%. And once I close the graph, it evaluates it on the 6 test images. And as you can see, this particular model gives us correct result for the 6 test images, representing the 6 categories of classification. And then we can move on to the next step, that is visualization of CNN. Now, visualization is used to understand the structure of a CNN model. Now, there are 2 methods that I want you to be familiar with. Both are reasonable in their own sense. Starting with the script way, this is visual Keras. This gives us a nice image so that we can understand each of the layers that we have used for our model. Let's run this particular script by providing it the path to our model. And once run, you will see an image pops up which displays the structure of our CNN model. And as you can see, the first convolution layer contains the largest in the size of a convolution model, but the thinner in the second contour layer. And the second contour layer is thicker than the first contour one layer, but it is smaller in size as it contains smaller, as it comes after the max pool layer. And for the flattened layer, you can understand that it contains a single dimension because it has flattened every n-dimensional data into a single dimensional data. And then we have the fully connected network composed of the 2 dense layers. The final layer contains the 6 output neurons. And this was one method of visualizing our CNN model. The next method is using the Neutron app. Using the Neutron app, all we need to do, instead of running a script, we simply drag and drop the model that we have trained earlier. So let's drag and drop that model over the Neutron app. Now, the difference here will be that the Neutron app will display a lot more detail about our CNN model. As you can see, if you hover over to the input, you will understand the dimension of our input. That is 30 cross 30. So this particular model takes in an input image of dimension 30 cross 30. And if you scroll down to the last dense output layer, or the softmax, you will look at the bias that is 6, representing the 6 categories of classification for this particular model. So the Neutron app displays a lot more data about our particular model, and you can understand a lot more about the intricacies of the input-output dimensions of our model. Also, if you look inside the contour layer, you can also see that it has 16 filters for the first contour layer. The second contour layer has 32 filters. So these are the 2 methods of visualizing any CNN model, and you have visualized what model that we have created in the previous video. Now that we have trained our model and it has achieved a reasonable accuracy on the test set and the training set, we can then move on to attaching this particular model to our sign detection module and seeing the results. So let's do that. All right. Now that we have trained our CNN model, let's add it to the sign detection module to complete the classification stage. We start off by declaring the classification variables and then importing the function of load model that will be used later. Then inside the detect sign function, before we have converted our frame to grayscale, we import our model from the data folder and then save it inside the model variable. Then once we have done that, we proceed inside the sign detect and track function. After we have localized our potential candidate, we try to classify the region of interest. But before we can pass this region of interest to the model to get the required predictions, we need to convert it into a format which the model accepts. To do that, we need to declare a new function that is image for keras. So let's do that. After we have defined the function of image for keras, we can now move after the localized sign and call that particular function of image for keras. We pass in the localized sign, and this gives us the output as the image format, which now the model will accept. So we call in the model, pass in this sign that is converted to the format, and then this gives us the output of the confidence score for each of the category that the model possesses. Now, to get to the prediction of the model for this particular input, we need to use the numpy function of argument max. Now, argument max will simply return the category by simply returning the maximum category with the maximum confidence score. So let's do that. We write numpy.argument max, pass in the model confidence scores, and then this will give us the output of or the category with the maximum confidence score. Now, to get from this confidence score or from the category value to the category name, we can simply pass on this to the classes or sign classes list that we have declared above as the index. This gives us the predicted signs from the model for this particular input. And once we have done that, we can proceed to the next step. For the next step, we simply check that this predicted sign is not a no sign, then we can simply display it in a green color, also displaying its category along with it. Once we have done that, we can now run this particular project by building it. So let's save this, proceed to the terminal, build it using the call build, run the simulation. Once the simulation starts, we run the computer vision node, and you notice that the car starts to move. So the star approaches this left turn and it makes this left turn, and then it will start to approach a potential candidate or potential sign. And once it approaches a potential candidate, it not only localizes it, but also classifies it all along with displaying its respective category. As you can see, it displays that speed sign 90 quite accurately, I might say. So this completes the classification stage of the sign detection module, and now we can proceed to the next step to complete our sign detection module on the whole, and then proceed to the control stage. Till then, thank you and bye. It's time we talk about the third tracking algorithm known as optical flow. Optical flow is the motion of pixels between the consecutive frames caused by the relative movement between the object and the camera. An example of this can be seen right here when a camera is trying to see this object. And to estimate the relative movement between the object and the camera, all we need to do is compute the movement of the pixels between two consecutive frames. For example, if we want to track this particular person, all we need to do is choose specific pixels on this person that we need to track in the consecutive frames. And once we have estimated their motion between those frames, we can now compute the relative movement between that person and the camera. So this was the theory behind the optical flow. And its usage is very simple, that we can estimate the motion of the objects and also track the camera itself relative to the whole scene. The second usage can be seen in this example right here. Here, the whole scenery is being tracked by choosing 4 points in the scenery. These 4 points are being tracked using the optical flow, and their final location is displayed in the next frame. This final and initial location are connected to each other by displacement vector. So once we have estimated the motion of these pixels in the 2 frames, we can now estimate the motion of the whole scene by displaying the displacement vector on the 2 frames. So the output that we got using the optical flow was the displacement vector for every pixel. And this displacement vector was describing the initial location in the first frame and the final location in the second frame. The types of optical flow are 2 in number. First is the sparse optical flow, and second is the dense optical flow. Starting with the first sparse optical flow, this is tracking only specific pixels in the whole frame. And because we are tracking only specific pixels, this is less computationally expensive. An example of the sparse optical flow can be seen right here, where we are trying to track the whole object or the vehicles by tracking only the specific point on those vehicles. And as you can see, these vehicles' movement can be tracked by only tracking these specific points, which are shown in these colorful trails, leaving behind the vehicle. The second example, or second type, is the dense optical flow, where we track all the pixels instead of the specific pixels in the sparse optical flow. And because we are tracking all the pixels, this is more computationally expensive than the sparse optical flow. And this is also the reason it is always used in the academic use only. An example of this can be seen right here, where we are trying to track persons in this scenario. And the tracked person can be shown in this colorful form on this black background. So how can we solve for the optical flow? One method for solving the sparse optical flow was described by the Lucas-Kennard, where he proposed that a method that relies only on the local information that is derived from some small window surrounding each pixel of interest. What he meant was that if you want to compute the movement of a pixel in 2 consecutive frames, what you need to do is rely only on the local information provided by the local window surrounding that region of interest or pixel of interest. So this was the idea behind the Lucas-Kennard method. And it was initially proposed for dense optical flow, and then it was later adopted for sparse optical flow. So how does Lucas-Kennard method work? Lucas-Kennard proposed 3 assumptions for solving for sparse optical flow, starting with the first assumption, that is, the intensity of the pixel does not change across subsequent frames. For example, if we have 2 consecutive frames, frame 0 and frame 1, then the corresponding pixels between these 2 frames will have similar intensity, because a small change in intensity with a small change in time is equal to 0. So this is known as brightness constancy assumption. Second assumption that he made was that temporal increments are fast enough relative to the scale of the motion in the image that the object does not move much from frame to frame. So if we have 2 consecutive frames, the information is updated so fast that the relative motion of objects between these 2 frames is negligible. So what he said was that a small change in the x or y direction performs negligible change in the intensity of the pixel values. To combine these 2 assumptions, what we get mathematically can be put right here. It says that the intensity at a specific location and a specific time is equal to intensity with a small change in location and a small change in time. And expanding on the right-hand side term, using the Taylor series approximation and keeping only the first derivative, what we get is this equation. Here the first term cancels out with the left-hand side of the first term. And this is equal to 0 now. And what we are left with is this first value and this second value multiplied with the change in x and change in y. This first and second value, let's call it a and b. These are just the spatial derivatives, as the change in intensity is related to the change in x or y domains. The third value multiplied by change in d is, let's call it c. C is known as a temporal derivative, as this just represents the change in intensity with change in time. So if we divide this equation by dt, what we get is the dx divided by dt, dy divided by dt, and dt divided by dt. And this cancels out, and what we are left with are 2 terms right here. The first, dx divided by dt, is a change in x with respect to the change in time, or the horizontal displacement with change in time. And second is vertical displacement with change in time. And what these are both velocity values. The first is the horizontal velocity component, and second is vertical velocity component. So this is known as dx divided by dt is also known as u, or horizontal optical flow. And the second is v, which is the vertical optical flow. These are the 2 unknowns that we are going to find out to estimate the motion of the pixels between consecutive frames. And this equation that we got right now is known as optical flow constraint equation. So what we need to do is find out these 2 unknowns in this particular equation, and this is an under constrained equation because we have 2 unknowns and only 1 equation. So we need more equation. How can we get that? For this, the Lucas-Kennard proposed another assumption. That was the neighboring pixels or points in a scene or image belong to the same surface, have similar motion, and project to the same point on the image plane. Right here, if you see this image, the same surface can be directed to the same point in the image plane, and thus they represent or have similar characteristics according to the neighbors. So what this means is we now have multiple equations for solving for the 2 unknowns, because all the neighboring pixels of the pixels that we want to track or estimate the motion of have the similar motion and have similar characteristics. So their equations can also be used to estimate the 2 unknowns known as u and v. So how he he solved this using the weighted least square fit of the optical flow constraint equations that we got. And minimizing this equation, which is right here, this is known as a weighted least square fit. And as you can see, this is of the form known as AX is equal to B. And here what we need to find out is the X term, which is the U and the V, horizontal and the vertical optical flow. To find out X, what we need to do is move A to the right hand side, and what this equation will become, X is equal to A inverse of B, because these are matrices. And to find an inverse of a matrix, we need to first check if that matrix is invertible or not. And this is the term that we need to check whether it is invertible to actually estimate the X terms. And to check the invertibility of a matrix, what we need to do is say that this is an A matrix, which is of the form A, B, and C, D. And we compute its eigenvalues using this formula. And once we have computed these eigenvalues, we can have three cases of these eigenvalues. The first is that both of these eigenvalues are greater than the threshold provided by the user, which represents a textured area, so an area that can be tracked, or a pixel that can be tracked, which means that the A is non-singular, that matrix is invertible, and we can compute the U and V values by solving using the Cramer's rule. The second case is where either one of those eigenvalues is larger than the threshold and other one is smaller. This represents an edge surface, which means that the A is singular or non-invertible, and we need to first normalize the gradient flow to calculate for the U and V. And the third and last case is that both of these eigenvalues are less than the threshold, representing a smooth surface, so U and V cannot be calculated and are assumed to be 0. So the idea of the optical flow, or the Lucas-Canal method for solving for sparse optical flow, was that we give some points to track and we receive the optical flow vectors at those points, which depends on the displacement of those points. And just like any other method, Lucas-Canal method also suffers from some limitation. That limitation is that this method can only be applied to slow-moving objects. For fast-moving objects, it violates a second assumption that we made during this method, that was of the temporal persistence. And what the temporal persistence said was that temporal increments should be much faster than the object movements. So if we have an object that is moving very fast, this means that it violates the second assumption, and thus this method cannot be applied to that object. The solution to this problem is known as pyramids. And to apply this solution, what we need to do is keep the original image at the bottom of the pyramid and compute the next layer of the pyramid by simply subsampling the previous layer. And this is followed to n number of levels. And once we have created the pyramid for each frame, then we can apply the pyramidal optical flow to estimate the motion of the pixels. To apply this, what we need to do is start from the right to the top of the pyramid, and this right to the top we can estimate the motion of very fast moving objects, because at this point those fast moving objects has become very small moving objects because the spatial reduction in those sub levels. And now we can simply move down to each level to compute the motion of slower moving objects right down to the original base layer. In this way, pyramidal optical flow estimates the motion of each pixels in the separate object that we want to track. So this was the theory behind the optical flow, and now we can move to its code flow. Once we have detected a particular sign, this will become the input to our tracking stage. And then we'll try to keep track of the location of that particular sign, preserving its identity in the process. Previously, we completed the detection of the signs, but the sign detection module is still yet to be completed. The reason is that we want to track those signs once they have been detected. So in this training session, we are looking to build a tracker class that will be used to track the signs once they have been deemed detected, as long as they are within the frame, of course. So for this reason, we'll move inside the detection folder and create a new file. This will be named as opticalflow.tracking.py. Now this particular function or file that will contain the tracker class is placed inside the detection folder and not inside the sign detection folder because of one primary reason. That is that we want the tracker class to be accessible to all the modules that may require it. Once inside the opticalflow.tracking.py file, we simply import all the libraries that will be used to create this tracker class. Then we simply declare our tracker class by writing class tracker. Then once we have declared it, we can now define the very first function that is crucial for any class, that is the init function or the initialize function. Now the init function will contain all the variables, all the instance variables that will be specific to each instance of the class. These are the state variables, for example, the mode of the class, representing the mode of the class that will be initialized to detection when the track class or the object for the track class has been created. Then we have the track class or the class that has been tracked for this particular tracker. Then we have the proximity variables. This basically represents all the variables, all the detection that have been previously done in the previous frames. Then we have the initialize variables. These variables will be used to initialize our tracker once we have confirmed our detection. Then we have the draw variables. These variables will be used to draw the tracking done in the previous frames. Then once you have defined instance variable, we can now define the class variables. Now the class variables will be global or accessible to each instance of the class, and they will not change through any instance. These are the feature parameters and the Lucas-Kennard parameters. The first feature parameters are simply the parameters that will be passed to a function that is good features to track, the function that will be required to instantiate the tracker class. Then the second function or the second parameters are the Lucas-Kennard parameters. These parameters will be passed on to the function to basically track our tracker class through the several frames. Now, once you define the class variables and instance variables, we can now proceed on to defining the second function, match current center to none. Now, this particular function is not directly related to tracking, but it will be declared inside this tracker class because it basically checks the validity of the previous detection. It does so by simply taking the center of the current detection and comparing it to the previous known centers. And if we have found a detection that matches the previous known detections, then that means that that particular detection can be said to be a valid detection because we have a pure confidence that that is a pure detection. And this returns us the match found and the index of that match. Once we have several matches, then we can be sure or we can be confident that that particular detection is a valid detection. Then, once we have a valid detection or we have verified the detection, we can now define the function of initialized tracker. And the initialized tracker will only be called once we have a confirmed detection. Now, inside this function, the very first thing that we need to do is simply set the mode now to tracking. Now, the mode of the tracker class will not be detection, it will now be set to tracking. So let's set that to tracking. So we set the self.mode to tracking. Then, the next thing that we need to do is set the track class to the sign that we have detected currently. Then, what we set is a self.oldGray, that is the previous image, to the current image. Now, once we have defined these variables or instance variable, the last thing that we need to do inside this initialize tracker function to initialize our tracker is simply extract all the points that we want to track in the next frames. And that can be done by CV2 function of good features to track. This takes in the image, that is the grayscale. Then we provide in the mask that represents the region of interest from which we want the good features to be extracted. This region of interest is the region of interest that we want to track in the several frames, or the sign in the actual case. So let's create that mask. We will create that mask using the start and end points, and then simply setting that area to 255. And then we simply pass on this mask to set this to mask is equal to sign mask. Once you have done that, we can simply now provide the parameters for these good features to track that are part of the class variables for this particular class. So let's do that. So we write double pointer self dot feature parameters. Once we have done that, we have provided all the arguments for this particular function, and what basically it returns is self dot p none. So we now have the points that will be used to track in the next frames. Once we have done this, we can now move on to defining the track function for this particular tracker class. Now, inside the track function, the very first thing that we need to do is simply use the Lucas-Kennard method to track the previous point in the current frame. So let's do that. So we call that particular function, that is calculate optical flow pyramidal Lucas-Kennard. It takes in the previous image, that is self.oldGray, that is then provided in the next image, that is gray. Then we provide in the previous points, that is self.p0, extracted in the initialize function, and then we provide in all the parameters that is specific to the Lucas-Kennard method. And that was part of our class variable. So we write self.Lucas-Kennard parameters. Once we have provided all the arguments to this particular function, all that is left or return this particular function returns to us are the points that have been tracked, the status of those points, and the error. So we don't require the error, so we simply set that to underscore. Once we have all the points that have been tracked, all that is left for us to do is check whether we have the points that have been tracked or there is no points that have been tracked. If no points have been tracked, then that indicates that the tracker has failed. So we simply set the mode tracking to detection and simply reset our tracker. Otherwise, if there was some tracking done, then we simply draw the tracking done in the previous to current frame by drawing a line from the previous point to the current point. Once we have done that, we have completed our tracker class. All that is left for us to do is simply define the reset function. Now, the reset function, all it does is simply resets our instance variable back to empty. For example, the proximity variable has been set to empty list, and the old gray or init variables have also been set to empty, representing the empty tracker class, as it is not tracking anything at this current point when this reset function has been called. So this completes our tracker class. Let's import it inside the sign detection module. So what we do is simply write from our optical flow tracking, import our tracker. So once we have imported the tracker class, we simply create its object by writing sign tracker is equal to tracker brackets. Once you have created the object, we can now move inside the sign detect and track function and simply check the mode of our tracker. That is sign tracker dot mode if it is equal to detection. So if it is inside the detection mode, all the steps that have been done under it needs to be done. So what we simply do, copy over all these steps and simply press tab. So all these steps are implemented when the sign tracker mode is detection. Now, what we need to do is simply move after when the sign has been detected, but it's not a no sign. So this is a valid sign. We can now move inside it. After displaying it to the user, we now simply check its proximity. This proximity can be checked by the function of match current center to known. So we take the center of this current detection and match it to the known centers. Now, if we have several centers that are within the same proximity, then that indicates a valid detection. For example, in our case, we say that if a particular detection has been detected more than 4 times, then that is considered to be a valid detection because we are pretty sure that there is a sign there. Now, once we know that we have a valid detection, we can now initialize our tracker by writing sign tracker dot initialize tracker. We need to provide in the sign of that particular track class. So what we need to do is simply use the sign classes. As the index of these sign classes, we need to provide the max index. This max index is basically the most confidence our known centers are for the previous known detections. So if we have 4 detections and 3 out of those 4 detections indicate a stop sign, so this is the stop sign that we are currently tracking. So we will say that this sign we are about to track is most likely stop 3 out of 4 times. So once we provide this first argument, we proceed to the second argument of the initialized tracker, that is gray or the current image. Then we provide in the frame to draw, and then we provide in the start and end points representing the region of interest that we want to track. Once we have provided this, our tracker has been initialized in this particular case. Now we need to address what happens if no match was found for the current detection. In that particular case, if this new detection that we have done has not been found in the previous known detections, then what we simply do is append it to the known centers. Also append its confidence by writing 1 because it is detected 1 time, and also append its class's confidence by converting the current detection to categorical by using the ROS function to categorical. Once we have updated these variables, we can now complete our detection mode for the sign tracker class. Now, once you have done for the detection mode, we can now proceed to the case when the sign tracker has actually been initialized to tracking. So let's proceed. After we have shown this and address the case of else, where the sign tracker has been entered into the tracking mode. So let's write here in the tracking mode. Inside the tracking mode, we need to call our object and simply call the function of track. Now, track function takes in 2 arguments of gray to the current image and the frame to draw those track points. Once you have done this, all that is left for us to do is simply display the track class. Once we have displayed the track class, our sign detection module has now been completed because we have addressed both the detection mode and the tracking mode. So once our sign has been detected and it has been confirmed to be a valid detection, it will start tracking that particular sign, and it will keep on tracking until it is within the frame. And once it exits the frame, that sign gets activated. So let's now build this particular module and see its results. So we write call build. We launch our simulation. Once the simulation starts up, we run the computer vision node. And what you will start to see that our car starts to move. Once the car starts to move, it will take the left-hand turn, and once it crosses that turn, it will encounter the first sign. Now, in the first sign, the very first step in the sign detection module, it localizes that sign, then it classifies it as a particular sign, and once it has been classified, it then starts the tracking, which is indicated right here by the speed sign 90 and these drawn lines. As you can see, it has been perfectly tracked. Now, if you observe the command line, you can see that this sign we are about to track is most likely 5 out of the 6 speed sign 90. So it was pretty sure that it was a speed sign 90, and it has been correctly tracked. Now let's observe what happens when it approaches the next sign. Now this particular sign is a speed sign 60. So first it will localize it, then it classifies it, and once it has been determined to be valid, it tracks it to the several frames, which is indicated by these colorful lines. And here you can see the sign we are about to track is most likely 4 out of 5, a speed sign 60. So as you can see, our whole sign detection module is working perfectly, and now we can move to create its control system so that we can finally create our second feature of cruise control. So till then, keep watching. Thank you, and bye. Finally, our self-driving car is able to now, based on the information that we have just acquired, we can provide the self-driving car with 2 basic but very important features that are: number 1, obeying the speed limits; number 2, navigating the T-junction. Let's tackle them one by one. Starting with the first feature, that was to obey the area speed limits, we have the following information. Here we can see the information being extracted from the speed signs in sign detection. From this, we are aiming to provide the self-driving car the ability to adjust its speed to comply with the area speed limits. And following are the constraints that we need to be wary of while proposing a solution. Number 1, our car can only obey the speed limits to which it is trained on. Any other speed sign will simply get ignored. Number 2, turning at high speed will still be a problem, so we need to adjust for that. Feature 2, obeying the area speed limits. Area speed limit is extracted in sign detection and saved in the track sign ID. For example, in this case, it is a 60. Before putting forward the proposed algorithm that will be used to obey the area speed limits, there are a few considerations. Number 1, we would need to set a global speed to which the car moves in normal mode. Number 2, the self-driving car speed needs to be modified against the received area speed limits. Number 3, we would need to adjust speed in turns. The proposed algorithm is: number 1, the global speed of the car is set to 80. This should be enough to counteract opposing forces of gravity and friction. Number 2, the speed whichever the car is running at needs to be reset to the track sign ID to comply with area speed limits. For example, if the car was running at 80 and it encountered and detected a speed sign 70, its speed should now be modified to 70. Number 3, in turns, the car might overshoot at high speeds. To counteract that, the speed of the car should be lowered so that it can make those turns easily. In coding the speed control feature, we will have the speed sign ID as an input, and we'll be modifying the current speed according to received information. Previously, we completed the detection stage for signs. We now extract the information regarding the current state of the car. This information will be leveraged inside the control state to complete the cruise control feature. In the current coding session, we are looking to develop a control system that can make the car obey the road speed limits. For this purpose, we move inside the drivebot.py and simply pass in the mode and the track class, the two outputs of the detect sign, as the current state of the car. Then, once we have passed in this information as the current state of the car, we move inside our control class, inside the drive function, simply unpack the current state to its 5 arguments, that is mode and the track class. Then once we have this information, we can simply pass this mode and the track class as the third and fourth argument of this follow lane function. Now the follow lane function is very interesting because it will in-house two things or two features that are lane assist and the cruise control. Then inside the follow lane definition, we also pass in the fourth and the fifth argument of mode and the track class. Then once we have defined these 5 arguments for the follow lane function, we can now implement the cruise control in 3 steps. For the very first step, we set the cruise speed of the car to 80 in the initialization function of this control class, along with setting a few other variables of previous mode and increase tire speed in turns boolean. Then for the second step, we move inside the follow lane function and simply check for the case whether a sign was detected and tracked, and then it exits the frame. This signals the change of mode for the sign tracker from tracking to detection, so the speed of the car now gets updated to comply with the local speed limits. For the final step of the cruise control feature, after we have extracted the angle of the car, we simply adjust the speed of the car in turns to overcome inertia. The idea is, the sharper the turn, the higher the speed should be. This completes the cruise control feature, and now we can simply build the project and analyze the results. So move inside the terminal, we launch the simulation again. Once the simulation starts up, we run the computer vision node. Now what you will observe is that once the simulation starts up and the computer vision node has started, it starts to move the car and make that left-hand turn. And then after it has made that turn, it will encounter its first sign. At the moment, the sign detected is displayed to be 0, indicating that no sign was detected as it has not approached any sign. And as soon as it detects that sign of speed sign 90, you can see that the speed sign 90 has been correctly displayed. And also displayed is the tracking trails of this particular sign, which has been tracked in the previous frame. As soon as this sign exits the frame, you can see on the top, the speed of the car has been adjusted to 90 to comply with the local speed limits. As the local speed limit was 90 for this particular road, so we upped our speed from 80 to 90. Then, when the car approaches the speed sign 60, it detects it and then tracks it, and then as soon as the sign exits the frame, signaling that it's on the road which has a speed limit of 60, it lowers its speed down to 60, which is evident on the top bar. Then it will keep on moving straight. Then whenever it approaches its third sign, it will adjust its speed to comply with the area speed limits. So as you can see, the cruise control is working accurately at the moment, whose prime purpose was to adjust the speed according to the speed limits of that particular area and also cruise at a specific speed. Along with this, you can see the terminal displays how sure it is about a particular sign being a sign. So 5 out of 5 is 100% surety for that particular sign to be a speed sign 90. And as you can see, as it makes this turn, the car will approach its third and the final sign, that is a stop sign. At the moment, the car is moving at speed 60, and whenever it tracks that stop sign, and then it exits the frame, this is the point the speed of the car gets modified to 0, indicating that the cruise control has worked accurately in every sense. As you can see, the car has literally stopped right here, which is also indicated by the terminal. And if you observe the simulation, you can see that the car has stopped just besides the stop sign, which is right where we want it to stop. So the cruise control and the lane assist feature both are working perfectly, and we can now move on to the next feature, that is navigating the T-junction. Till then, thank you and bye. Apart from the speed sign, there is an additional sign that we might come across. This is the left turn indicator. This signals the self-driving car how to navigate the T-junction by taking a left turn, as that is the correct path to go. Here we need to understand that there is only one correct path, and that is why the left turn was crucial for navigating the T-junction. Navigating the T-junction, detection of the left turn is the trigger point. Its location will be tracked until it disappears, signaling the point to make the turn. So we have drawn a direct one-to-one relation between the left turn and the T-junction. Following other considerations we need to make before putting forward our proposed method. Number 1, the relationship between the left turn and the T-junction and its location will be following a specific convention, 1-to-1, and placed just before the T-junction. Number 2, the T-junction size will be the same for easier rule-based navigation. Number 3, the car speed will be locked at a specific value for calculated turning. For the proposed method, once the car starts tracking the left turn, we set the car angle to 0 and keep it moving straight. We also set the car speed to 50 for predictable turning later on. Once the tracking fails, this is the time we start a loop, and on every 20th iteration, we move the car slightly left by modifying the angle a little bit. Once we reach the max iterations, we break the loop, signaling the end to the left turn. Finally, we keep the previous angle and speed until the lane detection provides its own data by redetecting the lane. Once the data arrives, we return the car to the lane follow mode. Junction requires the same information to be used that was extracted in the sign detection. That was the mode and the track class. Using this information to move inside the drive function, where we check for the left turn to be detected. If such a case arrives, we activate the left turn procedure. This is done by calling the obey left turn. Now, this particular function requires a balance of timing and precision turning and also a few constraints. Now, before we define this particular function, we need to set a few variables. That variable will be set inside the initialization function of the control class. Now, these are the previous mode left turn, indicating the previous mode of the left turn procedure, that is detection. Then we have the left turn iterations, indicating the duration that the left turn procedure has run. Then we have the frozen angle, indicating that the angle has been frozen for this left turn procedure. Then we have the detected and activated, the two states that the left turn procedure can be in. Now, we can simply define the function that will actually attempt the left turn feature, that is obey left turn. This takes in two arguments of self and mode. Now, the very first thing that we do inside this particular function is set the self.speed to 50. Now, the reason we set it to 50 is because we want to achieve that precision that we were talking about earlier by setting or making the car move at a steady speed of 50. Then we simply check for the change in mode from detection to tracking, because this indicates that we have confirmed left turn detection. So we now set the boolean of detected left turn to true. This means that we can now make the car move straight by setting the current angle to the frozen angle, which was initialized to 0. Now, once the car moves straight, we can then address the second condition where the mode or the tracking has been failed. This track failure of tracking indicates the start of the T-junction. So now we can simply let the car make that left turn and then keep on making that left turn by maintaining the steady speed of 50. The car maintains this increase in left turn till the maximum turn and keeps on moving until it redetects the lane, and then the lane assist feature kicks in to take its place. This signals the completion of the T-junction navigation. Now we can simply build this project by saving it, moving inside the terminal, writing qualcomm build, running the simulation. Now this particular simulation is testing the T-junction navigation. Now as you can see, the car here is at the start of this road, where at the end we have the left turn, right here. Now, what we want to do is simply run the computer vision node. Now you will notice that the car starts to move. Now, as the car starts to move, you will notice that the sign detected has been initialized to 0, so no sign has been detected as of yet. But as it approaches this left turn, it will change state from the 0 to detected left turn, which will be indicated right about now. Now, as you can see, the sign has been detected as left turn and detected has been set to true. This is that boolean that we were talking about earlier. Now, the speed has been set to 50 and the sign has been successfully tracked. Once the tracking fails, you can see the lane assist feature is no longer working, and now we have set the angle to decrease to -45, which is the maximum left turn. The car makes that left turn, which is indicated on the top, and then it redetects the lane when the lane assist feature kicks in. Now we have successfully navigated the left turn. So this means our third feature has also been completed. Now we can build our fourth and the final feature of crossing intersection. But till then, happy coding and bye. Fourth and the final stage of crossing intersection requires information taken from the traffic light. This information will be extracted in the detection stage, where we will follow the similar three stages as of sign detection. These were localization, classification, and tracking. But there will be a slight change in the algorithms we use for each of these stages. So why do we need to detect traffic lights for crossing intersection? Traffic lights are an important aspect of our daily commute. Negligence can lead to heavy-duty fines or serious road accidents. Intersections occur when two or more roads intersect at a point. These are often accompanied with traffic lights. So this means any self-driving car is incomplete without the ability to detect and respond appropriately to traffic lights and cross intersection as a result. In contrast to this, traffic light was a combination of several shapes. So why can't we use the same algorithms for traffic light detection as sign detection? Starting with the localization, the signs that we chose were all circular. So their shape was leveraged to localize circular regions in the image. In contrast to this, traffic light was a combination of several shapes, 3 circles and 1 rectangle. Secondly, for circular signs, perspective transformation could at max only distort it to an oval shape. In contrast to this, traffic lights can be distorted or have harrowing effects on its shape, which is certainly not desirable. These reasons lead us to believe that no single feature approach will be enough to localize traffic lights. Somehow, even if we were able to localize, classification of traffic lights using simple CNN would require us to train for 3 new classes: red, green, and yellow, the 3 states of traffic lights. Also, signs and traffic lights do not belong to the same category. This means that we would require separate models for each of these classes. So these are some of the problems we need to look into while designing a solution for traffic light detection. Hard cascade is an object detection algorithm that has both high accuracy and low computation cost. It was first proposed by Boyle and Jones in 2004 on a relatively weaker platform as of Pentium 3 and still ran on an astounding 15 frames per second. Such speed, while still maintaining accuracy, was unheard at the time. So why is hard cascade still relevant today? Unlike modern deep learning solutions, hard cascade is reliable even on weaker platforms. And we also have trained models available for some very important tasks, such as face detection. The core concept of the hard cascade algorithm is that instead of using a single complex classifier, we will be using a cascaded bunch of simpler, smaller classifiers. And the 4 steps of the hard cascade algorithms are: number 1, hard features; number 2, integral images; number 3, add a boost; and number 4, cascading. For the algorithm, starting with the hard features, Boyle proposed that instead of looking for the complex features, look for the simpler ones. For example, in face detection, CNN would have probably looked for complex features to identify a face, such as the eyes, the nose, and the mouth. Instead, the hard cascade will be looking for regions that are brighter or darker than the other. For example, the nose bridge is darker than the cheeks, the eyes are darker than the forehead. These are known as the hard features, and they can be computed or calculated by simply subtracting the sum of one area with the sum of another. So if we wanted to identify the nose of a person, all we need to do is use this hard feature A and convolve it over the person's face, and it will give the maximum response when this hard feature A is placed right above the nose bridge and the cheeks. So we have identified that the hard features were calculated manually instead of the automatic way used in the CNN. And we had fewer initial features, and the rest were calculated by resizing and reorienting them in several ways. We got around 180,000 features for a face detector that was of 24 x 24 size. So once we have identified the information required to detect the object, the next step was to reduce the compensation and increase the efficiency of the process. So we have identified that hard features were calculated by subtracting the sum of an area with the sum of another. What if we could find the sum of an area quicker than the iterative speed? Introducing integral images. Integral images are computed by simply summing everything that is above and to the left in the original image in that specified coordinate. For example, for this particular image, we have computed the following integral image. How this was calculated can be seen right here. For the 0th index in the original image, we have the value 31. There is nothing above and to the left of this original image, which means that this 31 will get added to 0, amounting to 31 in the first index of the integral image. For the second index, that is 0th row, first column, we have 2, and to its left, we have 31. This amounts to 33 if we sum them up. If we go one row down, we have 12, and to its above, we have 31, and to its left, we have again 0. So 31 plus 12, we have 43. And for the first row and first column, we have 26, and to its above, we have 2, that is 28, and to its left, we have 12, that is 40, and to its leftmost, we have 31, which, summing them all up, we have 71. So this is how the integral image is computed for the original image. Once we have the integral image, the computation time of big O of n for finding the sum of an area is taken down to only 3 operations: 2 subtraction and 1 addition. To see an example of how integral image can be used to find the sum of an area with only 3 operations, let's take the example of this orange region. So we want to find the area of this orange region, which can be done either iteratively by summing the 15 plus 16 plus 14 plus 28 plus 27 plus 11, amounting to 111. this was taking 5 operations as it was having 6 values. But using integral image, we can take it down to only 3 operations. So how this is done is simply, first we take the sum of everything up until that region that we want to calculate the sum of. So for this colorful region, we have the sum right here in the bottom right corner, that is 450. 450 gets the first value, and we will subtract the 2 values, the first being the blue and the green region, the sum of the blue and the green region, and the second value, the sum of the green and the yellow region. So this amounts to 254 and 186 respectively. Once we have subtracted this blue and the green region and the green and the yellow region, the one thing to notice here is that we have subtracted green region twice. We only wanted to subtract it once because it was only coming up once. So we need to add it to nullify the twice effect. So to add it, all we need to do is use its sum value, that is 101, in the integral image. Now we sum this 101 in the final value, which gives us to the 111. This means that we have computed the same sum of 111 by taking only 3 operations, and this will always take 3 operations, regardless of how big the image or the region of which the sum we want to calculate. So this is why the integral image performs the crucial role of reducing the computation time of the algorithm and increasing the efficiency of the process. A critical component in making hard cascade an efficient algorithm was ADA boost. The concept was to exclude large number of less important features and only focus on the most important ones. This meant that we only required 2,500 features instead of the 180,000. This was a reduction of a whopping 98.6% overall. Mainly, there are 2 things that ADA boost does. Number 1, helps to choose the training set for each new classifier that you train based on the result of the previous classifier. Number 2, determines how much weight should be given to each classifier. This means that the most important classifier would be given the most weight and will be sorted out from the rest. Cascading. The idea behind the cascading is that the focus and the computation should be given entirely to those regions of the image where the object is likely to be. How this is implemented can be seen right here. Given an input image, we move our 24 cos 24 detector all over the image and try to compute the 2,500 features for each of those windows. So if the cascade does find a face, we move along to the next cascade. Otherwise, we simply discard that region. This means that the focus is entirely on the region where the object is most likely to be. All other regions will simply get discarded early on. This means that the time complexity is reduced because of this method, and structurally, this is essentially the same or resembles that of a degenerate decision tree. In summary, the following step would be required for the detection using Euler-Jones algorithm. Initially, we would need to train the hard cascade algorithm and store its weight somewhere on the disk. Then, during detection, these weights of features will be loaded from the disk and applied over the image, trying to find the object. Finally, the cascaded classifier moves over the image, trying to locate the object. When all the cascaded classifiers are activated, this signals the detection of the object and its location is retrieved. Hello guys, it's time we build the fourth and the final feature for our self-driving car, that is crossing intersections. For this, we require the information that we as driver use to cross the intersection, that is from the traffic lights. So in this training session, we are looking to develop a traffic light detection algorithm, and this will be achieved using hard cascades. So for this purpose, I've created a folder inside the detection folder, that is traffic lights. Now this folder will implement the traffic light detection module. Inside it, I've already placed a hard cascade folder which contains 2 things. The first thing is a training folder which contains all the files that are necessary to train a hard cascade from scratch for any object. And the second folder is a safe cascade that is simply the train cascade that can be used to perform the traffic light detection by any user. We will start off with the training, and for this, we will use the README that is present inside the hard cascade/training. Now this README starts off with the very first step, that is gathering the training videos from the ROS2 simulation. Now, as I've already done this step, that is, I've already gathered the videos that will be used to train the hard cascade as they are present inside the training folder, which is the videos folder. Inside the videos folder, you will notice these 5 videos, which are the actual videos that will be used to train the hard cascade to detect for traffic lights. Now we can proceed to the next step, that is extract frames from videos using the function by importing from training/utils.py. Now, the utility.py function or Python file simply contains all the utility functions that are necessary to train the hard cascade, starting with the first function, that is extract frames from batch. So to extract this particular frames from batch, we require this function. So we first need to navigate to the training directory, open a terminal, open the Python terminal by writing Python 3. Once inside the Python terminal, we can write from utils import every function that it has. Once we have done that, we simply copy over the function name, that is extract frames from batch, paste it, provide the video directory as an argument, that is videos, and then press enter. What it starts doing is it starts extracting the frames from all the videos present inside the video directory. As you can see, if you navigate to the video directory, you will see the extracted frames started to fill up. It will contain all the frames that are extracted from those videos present inside this folder. Once we are done, we can proceed to the next step. For the next step, what you will observe that it is to sort the frames present inside the extracted frame folder into positive and negative data and place them inside the positive and negative folders respectively. So this step requires a lot of manual thinking. So as I've done this already, so that it can be done quickly. So this positive and negative direct data has already been sorted and placed inside this positive and negative folders. If you navigate to the positive directory, you will observe that all these images will contain the traffic light, which is our region of interest. So this is actually the positive data. And if you look on any other image, you will observe the same pattern. And if you look inside the negative directory, you will observe that this contains all the information of the simulation except the region of interest. So this is our negative data. Now you need to do this sorting manually, but I've done this already, so I've just shown you what it looks like. Now we can proceed to the next step, that is visualize the data, and that can be done by the function count files from DIRs or directory and subdirectory. You simply copy over this function, navigate to the terminal, paste it, and simply write brackets. Because we are in the current working directory, which is a training folder, this contains the positive and negative data, so we simply need to call this function. And what it simply does is displays a nice looking graph that displays the balance of the positive and negative data. As you can see, the data is quite nicely balanced. To be precise, the positive images are 234 and the negative images are 259. So we don't need to augment any more data because the data is already balanced. We can proceed to the next step. For the next step, that is, it can be done from the step 4 onwards. It can be done by following a script file for each platform, that is Windows and Linux. As we are inside the Linux, we have the script file, that is Linux autotrain.script, which executes all the remaining steps to train our hard cascades. But there's one caveat in trying to train this hard cascade on a Linux environment. It requires OpenCV 3.4, and that also built from scratch or built from source. But as I have Ubuntu 20.04 and it has OpenCV 4.2 installed, so we cannot perform the remaining step on this Linux environment. Either I need to install or build OpenCV from source or OpenCV 3.4 from source, or we can follow all the remaining steps inside the CUOI environment. So we'll opt for the second option, that is moving inside the CUOI environment and trying to train our hard cascade from there, from this step onwards. So let's do that. So the next step is simply navigate to the training inside the CUOI environment. So let's do that. So I need to share everything that I have present in this local directory for this hard cascade training so that you can perform all the remaining steps inside the CUOI environment. So this is a directory that will be shared to you, that is the hard cascade training. It contains all the files that are necessary to train the hard cascade. Now we move inside the CUOI environment, that is this train hard cascade CUOI file, and it starts off with setting up the environment. We need to also link our Google Drive, which will contain our hard cascade training folder, and it is open on the left-hand side. So the very first thing that we need to do is simply set up our CUOI environment. So to do that, we simply execute this step, which is uninstalling the current OpenCV Python version, which is 4.2, as mentioned by this location, and then installing the OpenCV 3.4.8. Because this OpenCV 3.4 is required for a few applications that are necessary to run or train our hard cascades. Now, as you can see, the files is not showing at this moment. All we need to do is simply click this connect to a hosted runtime, and it will get displayed. And then we navigate to our directory, that is hard cascade training. Now inside this, you will see all the files that are also present inside our local directory of hard cascade training inside our repository. Now after this, we can simply navigate to the next step, that is check our current OpenCV version, which you can see is OpenCV 3.4.8. Now we can simply navigate to the next step, which is step 4, which was navigate to the path to training, that is hard cascade training. Now this will be different for where you have installed or copied over this folder for hard cascade training. So changes for your particular training method. If I execute this, it simply navigates to that folder, which is this folder inside my drive, and then it simply executes the from utils, import all the functions inside that utility file. Once it has done that, we execute the step 5, which if you look in this, our readme, that is to generate the negative.txt from the negative samples present inside the negative directory, inside the training directory. Now all it requires is a negative directory location, which is like this. So we simply call this function inside our CUOI and simply click this. And as we do that, the negative.txt gets generated. And if you refresh this, you will see that the negative.txt has been generated inside our hard cascade training. Now right here, if you click this, you will notice that it contains all the directory information of all the negative images present inside the negative directory. So if we close this, and we can simply proceed on to the next step. For the next step, if you look on the README, that is to generate the positive.txt file. Now for the positive.txt file, there are two methods to generate it. Because the positive also contains the region of interest, this text file will not only contain the relative directory of all the positive images, it will also contain the location of the region of interest inside those positive images. So we require a rect after those relative directories. So for this, we have two methods, either to annotate the positive images by ourselves using OpenCV annotation, exe, that is the application provided by OpenCV 3.4. And the other method is to create or augment the positive images or annotated positive images by ourselves by only a single image. This is an automatic method, the first step, and the second method is a more manual method of annotating positive samples. We will opt for the first step because the first step can only be attempted by inside the CUOI. And the reason is that the second step cannot be attempted because the second step opens an application or a graphical user interface that the CUOI does not allow. So we can only attempt the first step inside our CUOI environment. So we simply execute the OpenCV create sample, providing the image that is the positive.jpg. This will be present inside our augmented positive samples, and we provide the background as a negative.txt. Now negative.txt contain all the relative directory locations of all the negative images. And for the info, which will be generating the positive.txt, we name it as a positive.txt. This will contain all the annotated positive images information. And then we provide how many positive data we want to be augmented, that is 128. Then we provide the x angle, max y angle, and max z angle. These are simply the distortion that we want to apply to generate augmented positive images. And then we have the background color and background thresh that we set, and then we have the width and the height. Now the width and the height, here I have set to the aspect ratio of 3 to 1. And the reason is our traffic light is an aspect ratio of 3 to 1. Now if you navigate to our CUOI, you will notice that these have been set to the same values that I mentioned inside the README, apart from this image that is positive sample / positive.jpg. This is our image that will be used to generate or augment positive images. Now what it does is, when I execute this command, it simply overlays these positive images by distorting them a little over the negative images and generating the positive.txt file. So once it generates it, you will see that the hard cascade training folder gets filled up with all those augmented positive images. And then once it has done that, it will contain or create that positive.txt file, which will contain all the information about the positive augmented images. Now, once we have done that, we can proceed on to the next step. Now, this next step simply demonstrates why we cannot use the OpenCV annotation. If you run this particular command, that is OpenCV annotation, that is used to annotate the OpenCV images that you already have. For example, the positive folder images. The problem occurs that we cannot open display, which is a caveat of the CUOI. So either you need to perform annotation on a third-party app and then convert it into an OpenCV format and paste that positive.txt file inside this directory. Otherwise, you will have to follow the augmentation method. Now, as you can see, the above method has run successfully, and we have now generated all the images. If I open one of these, you will notice that how these images have been generated. Now, if I expand this, you will notice that the images that the positive.jpg has been overlaid over the negative image, and this has been creating a augmented positive images. And as it has augmented, or as this has created this positive images automatically, it also knows its location precisely. So it has created the positive.txt file mentioning its location in this particular image. So once we have done that, we can proceed to the next step. Now, if I show you the positive.txt file, you will notice what I mean. Now, inside the positive.txt file, you will notice that instead of the negative.txt file, which only contains the relative location of each positive image, it also contains the region of interest or rectangular region of interest representing its location in the positive image. Now, once you have done that, we can proceed on to the next step. So now we have generated the negative.txt file, the positive.txt file. We only need to perform or create the positive description file. So that can be done by providing positive.txt file to the OpenCV create sample once again. If you look inside the README, this is known as the step 7, which is generating positive samples from the annotation to get a vector file by executing this in command. This takes in the info positive.txt file, its width and height, and the number that we want to create, and this will create the positive.vec file. So we simply execute this command, and what you will see that it will give the error of the value that it has created 228 samples from those positive.txt file. Once you have done that, if you refresh this, you will observe that this gets created inside our hard cascade training folder, which is this positive.vec file. Now, once you have done that, we have all the information that was required to train the hard cascade, and we can actually start the hard cascade training process. And that can be done by the OpenCV application, that is OpenCV train cascade. If you click this, it will start the training process, but first we need to provide a few arguments. The first argument is simply the folder, that is a data folder, which will contain all the outputs of the train cascade. So I set it to cascade present inside the training folder. Then we provide in the positive vec file, which is present inside the main training directory. Then we provide the background, which is the negative.txt file. Then we provide in these two pre-calculation value buffer size is basically just for this improvement or increasing the efficiency of this process. Then we have the negative or number positive images, that is 200. Now this particular value needs to be precisely less than or equal to the positive images that we have present. As we created 228 samples, so we have written here number positive as 200. We cannot write here 229 because we do not have 229 positive samples. For the negative images, we can write any number that we desire, but as we have created 250 negative images, so I can write 400 and it will run just fine. For the number of stages, I let it run for 8 stages, and then I set the width and the height, which is of the aspect ratio 3 to 1. Then we have the maximum false alarm rate, which is the maximum false alarm rate before the execution stops or the training stops for this hard cascade. Now, if I run this, what you will notice is that the training starts to work. Because I have already trained this, you will see that it says that the training parameters are preloaded from the parameter file in the data folder. And if you want to set a new, you will need to empty the folder, that is the cascades folder. Now, if I navigate inside the cascades folder, you will see that there's already each stage present inside this cascade folder. This is the result of each stage of training the hard cascade from these positive.vec file and negative.txt file. Once their execution stops, which I can stop right here because I don't want you to continue for another hour because it might take a while, I can simply proceed to the next step. The next step, what I do is simply that because I have up to 6 stages already completed, I simply change the number of stages to 7. So this simply says that stages 0 to 6 are already loaded, and it creates the cascade.xml. Once this cascade.xml has been created, I can simply test this out using a video that is present inside my training directory. Now, when I execute this, you will see the results. But I've also trained a train cascade previously using the annotated images instead of the augmented images. Now, I want you to display a fundamental difference of using annotated images and augmented positive images. If I use the train cascade that was run or trained using annotated images, you will see that it will run flawlessly. And as you can see on this particular video, it gives us a great annotation or a great detection of the traffic light, which is a very tight boundary around this traffic light in each of the frames present inside the video. Now, if I stop this right here, you will see when I run the same process using the cascade that was trained using augmented positive images, it will not give me very good results. Now, if I run this using the cascade.xml, testing the same video, you will see that it will miss a lot of these detection. And the reason is very obvious. As you can see, it's not a very tight net around that image, and it is also giving us a lot of false negatives. If I scroll down right here, you will see that it does get a few detection, but it also misses them. And even the detection that it does do is not a very good detection. So there will be problems when you use augment, or you try to augment the positive data or augment the positive annotated data. It will not give you very good results. So if you want the best results, you need to annotate the positive data yourself by using a third-party positive annotation tool, or using the OpenCV annotation tool if you build the OpenCV 3 from source. So this is the result of training the hard cascade for a detection algorithm that tries to detect a traffic light. Once I've done that, this completes the hard cascade training, and we can simply import this train cascade, the one that was working better than the other, inside our main module of traffic light detection, and then see the results. All right, guys, so we have actually discussed the theory of the hard cascade algorithm, and now it's time to actually train the hard cascade and see for ourselves how well it performs in our case. Now, the hard cascade training that will be done is for the traffic light exclusively, but the same procedure will be followed or can be followed if you want to train for any other object. Now, moving on to our GitHub repository, here we navigate to the training directory in the hard cascade inside the traffic lights. So right here, what you will observe is that we have several files that will be required to train the hard cascade, along with a folder of cascades named as cascades. Now, at the moment, this folder is empty, and all the rest of the files are necessary to train the hard cascade. But once the hard cascade has been trained, that will be stored inside the cascades folder, and from that we can access it and use it in our project. Now, moving down, you will observe that we have a readme.mg file that simply specifies all the steps that are necessary to train the hard cascade for ourselves. Now, starting with the first step, what you will observe here, one thing I need to mention here is that these steps are mentioned for the Windows platform, but the same process can be followed for the Linux platform with a few alterations. But starting with the first step, that was to gather the training videos from the ROS2 simulation. Now, for the ROS2 simulation, obviously, we need to move to the Linux platform. And from those, we need to run up the ROS2 simulation and gather videos from that. And once we have gathered videos, we'll move or copy those videos and then move on to the next step. So I've already taken those videos, and they are stored inside the videos folder. But at the moment, if you move to the training directory, right now, we don't have any videos folder. But I will just simply copy the videos folder right here. So once copied, what you will observe is that it contains 5 videos or 5 training videos that will be used to train the hard cascade. Along with this, we will have an empty folder of extracted frames. Now, this folder will come handy later on. Now, once we have the training videos, we can move on to the next step. The next step is to extract frames from the videos using the following function by importing from training/utils.py. Now, what is the utils.py? Utils.py is a Python utility functions that are provided inside the training directory to train the hard cascade. If I open this, you will observe that we have several functions that will come useful when training the hard cascade. You can open them up and see for yourself how they are defined, and how you can tweak them for your own liking. But moving on to the command prompt, what we need to execute is that we need to use this particular function of extract frames from batch. Now, as this name implies, this particular function simply extracts frames from a batch of videos that we have provided in the training videos in the previous step. Now, for this reason, first we need to move to the command prompt, navigate to the training directory, and then enter the Python environment by writing Python. Once you have entered the Python environment, we simply import all the functions inside the util folder or utils.py file. From utils, import steric. Now, this imports all the functions present inside the utils.py, and then we simply copy over the functions that we would require and then specify the videos folder. And now we will specify the videos folder in its parentheses. Now, the videos folder name, if you look back in the training directory, was vides, small case in our case. So you need to provide the location or relative directory location or relative location of the videos folder, and then press enter. And then you will observe that it starts saving each of the frames in all of those videos inside the extracted frames present inside the training directory. Now, if you scroll down to the or move to the videos directory, and then inside the extracted frames, you will observe that now we have extracted frames that are being extracted using the function that we have just executed. Now, these are the frames that we were requiring to train the hard cascade. But at the moment, they're not sorted, so we need to sort them out, which is exactly the next step. That is to manually sort frames from the training video extracted frame into positive and negative data and place them inside the positive and negative folders, respectively, inside the training directory. Now, at the moment, you may observe inside the training directory, there are no positive and negative folders. So first, what we need to do is simply create empty positive and negative folders. Once I've created the positive folder and the negative folder, I can simply open them up and then simply start moving the positive images from the videos from the extracted frames folder. And once I've copied all the positive images, then all that's left are the negative images, and then I can simply move them to the negative images directory, and then we will be done with the sorting. So let's do a few images and see how we'll be going about this. So let's pick a few images that contain the traffic light, because those are our positive data, because it contains our positive or our region of interest that we want to detect. So that is why it's called the positive directory data. So let's take these 5 examples and then move them over to the positive directory that we have just created, like this. And once I move them over, not copy them, move them over, this simply removes them from the original directory. So once I've done with all the positive images, what's left in the extracted frames are all the negative images. Then I will simply copy those leftover images to the negative directory, and I will be done with the sorting. So to simply speed this up, let's move back to the training directory and simply copy the already sorted data into the training directory that I've done before. So in this way, I've copied, I'm sorry, I've given it the wrong name to the positive directory. I'm sorry. Okay, once I've sorted all the positive and negative data, I can now move to the next step. Now, the next step is to visualize the data. So whatever data they have created, I need to visualize it to understand how well it has been balanced. If it was not balanced, then I need to augment some data to balance that data set. For this reason, we'll be using the function count files in ders and subders, and its arguments are the path to training and the display bar. Now, at the moment, we're already inside the path to training. So all I need to do is simply call this particular function, and we write this function and simply call this function. And what it will do is simply look inside the training directory and look inside the positive and negative folders and simply display their values and their amount and display them in a nice looking graph. And as you can see, the negative or the positive images are less than the negative images indicated by the red color. So how much less can be observed in the command prompt, where you can see that positive images are 234 and the negative images are 259. So a difference of 20 images, which is not enough or not too much considering the whole proportions. So at the moment, we don't need to augment any more data set, and we can just go with this particular data set. So let's close this. All right. Let's close this and move on to the next step. The next step and the step onwards can be done either 2 ways. They can be done either manually, or I've provided you with a new method, or the automatic method of using the scripting files. So for the Windows platform, we'll be using the batch file, and for the Linux platform, you can use the script file. Both files are present inside the training directory, if you observe right here. So this is the Linux script and this is the Windows script. And what these scripts are doing are simply executing the remaining particular steps automatically, so that you don't have to do them manually. So let's look at what are those steps that we'll be executing. But before that, let's start the batch script so that we can follow along each of those steps that it is executing. So for this reason, we first need to provide the name of the Windows batch, because we're in the Windows platform, and then provide the location of the OpenCV binary directories. Now, the OpenCV binaries need to be downloaded from the OpenCV website, and then we are using the OpenCV version 3.46, which I would prefer, or I will recommend you to use this particular OpenCV so that you won't get any conflicts. Now, let's move on to the OpenCV directory. But before that, let's exit from the Python environment by hitting Ctrl+Z and then pressing enter. Once I've exited the Python environment, all I need to do is simply call the Windows train.bat, because we're already inside the training directory. So Windows auto.train.bat is present inside that training directory. And then I need to provide the location of the binaries of the OpenCV that I've downloaded earlier. Now, this is the location I need to provide. In my particular case, yours will be different of where you have downloaded your OpenCV version. Now, this binary directory contains a few applications that will be necessary to train the hard cascade. But those applications are OpenCV annotation, OpenCV create samples, and OpenCV train cascade. Now, for example, the OpenCV annotation annotates the positive images, which is basically specifying the region of interest in the positive images which we need to detect. OpenCV create sample simply creates samples from those annotated images, and then OpenCV train cascade trains the R cascade from those positive and negative data. Now simply provide this OpenCV binary directory to this train.bat, and the same process will be followed for the Linux train.bat. You will provide the binary directory to that particular Linux script, and then press enter, and it will start executing the first step. What that step is exactly, if you move to the fifth step, is generate negative.txt file indicating the negative samples directory to the following by the following command. Now, what this following command is simply using the generate negative description file from the negative directory. Now, it is simply creating a negative.txt file that simply specifies the directory of each of the negative images present inside the negative directory. Now, let's see if that negative.txt file has been created. And right here, you can observe that it has been created, and it contains or specifies all the relative directories of all the negative images that was present inside the negative directory. So once I've created this negative.txt file, we can move on to the next step. So let's look at the repo. What is the next step that our Windows train.batch is executing? The next step is to generate the positive.txt file. And how it will be done, can we look at this B part? That is, if you have all the positive images sorted already inside the training.positive, then generate the .txt file by executing opencv annotations.exe and provide the location of the positive.txt file where you want to store the text file, and then provide the location of the positive directory, which is the positive P, capital P, positive. Now, when I press enter, it will execute this, and opencv annotation is the application that simply is used to annotate all the positive images inside the positive directory. Now, why do we need to annotate the positive images? This can be understood once we understood the reason of what we are trying to achieve in this particular task. What we're trying to achieve right here is that we want to detect a specific object that contains not only classifying that particular object, but also localizing it, which means that we need to identify where that object is. And for that reason, the positive images are not enough to detect that particular object. We need to also specify where that particular object is in that particular positive image. So this is what's called annotation, is specifying that object in the whole positive images. And how we do this is simply specifying by pressing the left mouse button on the top of the region of interest that you want to detect, and then pressing the left mouse button again at the end of the region of interest where the region of interest closes, and then press C to confirm that selection, and then press N to move to the next window. And then we repeat the same process by pressing the left mouse button at the start of the region of interest, which is the traffic light, then press left mouse button again at the end of the region of interest, that is the end of the traffic light, then press C again to confirm that selection, and then press N again to move to the next window. We repeat the same process for the rest of the images, which are almost 239. And once we are done with all of the images, then we can simply move on to the next step. So be careful with the annotation. You want to stick good annotations so that your R cascade can train very accurately. Now, these are 239 images, so I'm not going to do all of them. I've just shown you the method, and I will simply skip this by pressing the exit button. But beware, pressing the exit button will cause a lot of problems, because you have specified in the later command that come after it in the automatic method a specified amount of images. So there are two methods that you could use. Either you could do it manually from this frame onwards, or you could use automatic method and simply annotate all the images that we have provided. Those are the 239 images that we have extracted from those videos. Now, at the moment, if I skip this by pressing the exit button, you will see that the next step gets executed, that is to generate the positive samples from the annotations. What this step was doing, if you look right here, generate positive samples, the seventh step was doing from the annotation was to use annotated positive data set, and then use the positive samples, annotated positive samples data set to create the positive samples and store it inside the positive.bag file. This is the extension that OpenCV used to train the R cascade. Now, for this particular reason, here we have provided a particular number of positive samples that we want to generate. And if we have provided incorrect text file, positive.txt file, or the annotation was incorrect, which in this case was incorrect because we have pressed that exit button, this will cause a problem, or it will get stuck at this particular step, which you can observe right here. It is stuck at creating training samples from image collection. And the reason it has gotten stuck can be observed when you observe the positive.txt file. So when you observe that what is positive.txt file, it not only contains the location or the relative location of the positive images, it also contains the coordinates of the region of interest that we want to detect in our positive images. But the error lies in the last entry that we have given, is that the last entry does not specify any region of interest that you want to detect in the positive image. This causes an error when generating the positive.bag file. So this, either you could do it by simply removing this particular line, that is the error line, and then moving or proceeding from this step onward manually, or you could do all the annotations that are present inside the positive images so that you don't get any entry that has any zero in it, and you can get all that steps done automatically without getting an error. But at the moment, because we have already done this, so we'll have to close this and do the next step manually. But we'll just skip this and just move onward by pressing the Control-C button. And it will ask to terminate the batch job, but I don't want to terminate it. So I will simply say N, which says no, and then press enter, which simply skips to the next step. But it will create a positive.bag file, which you will observe right here. But this positive.bag file is incomplete and is often error prone, so we'll not get any training done from this positive.bag file. But this is what this step does. It creates the positive samples from those positive.txt file that contains the annotations. Now, moving on to the next step is to configure the parameters in the following command and start training. Now, if you observe what it is calling is OpenCV train cascade. Now, this is the particular application that actually trains the R cascade. Now, there are several parameters that you need to tune, and they will be specific to your particular circumstance. But for this particular circumstance, I can mention you what are the parameters that I have set in our particular case for training the R cascade for the traffic light. Now, these are that the first parameter was to minus data that specifies the location of the trained hard cascade once the hard cascade has been trained. So I will store the trained hard cascade inside the cascades folder. And the next file is the vec file location, that is the positive.vec that you just generated in the previous file. The next is the negative.text location, or the background, the negative BG that specifies the background images location inside the text file. And then we have the buffer size that we provided so that we can speed up the training the hard cascades. And then the next arguments are the number of positive images that we have provided. And I have set this to 200 because we had 239 images. So we need to provide a number that is smaller than the maximum number of images that we have annotated. But at the moment, by showing you or training this particular hard cascade, I've only annotated 10 images. So this is the reason that we will get the error, the previous error, and the error that come after it when training the hard cascade, because we have written in the command that we are providing 200 images, but we have not annotated those 200 images, which causes the error in the previous state, and it will also cause the error when training the hard cascade. Then we have provided the number of negative images to 600. So we have specified that we are providing 600 images. Now this does not matter. It can be more than the negative images that you're providing. At the moment, you are providing around 259 images, negative images, but 600 works fine, because any number greater than the number that you provided will work fine, because it will make more or augment more negative images from the images that it already has. Then you need to provide the number of stages that you want this particular training to go on. I've specified it to 8. And then comes the width and height of the region of interest or the windows that will be detecting the hard cascade. At the moment, I've set it to 72 and 24, which is the aspect ratio of the traffic light, which indicates that the traffic light height is almost 3 times less than its width. So this is very specific to the traffic lights. Whatever case that you have, you need to analyze its aspect ratio and set it accordingly so that it can get a better detection. Next, the last particular value is the minimum false alarm rate, and 0.08 it is set to. Now this is very specific to our case. You need to adjust or tune this particular parameter to your particular case or whatever object that you're trying to detect. Now, once we start pressing the enter button, it will start the training process using the train cascade application, and it will give you an error. And what you'll observe is that the reason that the error came was that the most possible reason is the insufficient count of samples given in the vec file. Now, I've mentioned previously that we have not annotated completely all the data that was present inside the positive directory. So this is the reason this error has came, and we cannot do anything right now. The only thing that we could do is go back, annotate all the images, and then come back to the training part again. So this is how the training process can be done for training the hard cascade for the traffic lights, but the same procedure can be followed for any other object that you want to detect using the hard cascade algorithm. Now, once you have trained the hard cascade algorithm, as we mentioned previously, in the negative data command, that all this gets stored inside the cascade folder. So at the moment, I've already stored a trained cascade inside this cascade folder, and it's the same way that you will get a trained cascade being saved inside this directory, and you will use this trained cascade to test it out how well it performs in the real scenario. And for that reason, we move on to the last step, that is to test the trained cascade. And it requires another function from the util, that is to test trained cascade, and we provided the test video, and then we provided the location of the trained cascade. Let's copy this over. But before that, let's move inside the Python environment again, because this is a particular Python function. So once you have inside the Python function, we import all the functions available inside the util.py file by saying import steric. Once you have imported everything, we simply copy this over. Oops. We copy this over and then specify the exact location of the video that we want to use as a test video. So I will use one of the training videos, but you can specify any video right here to test it out how well it performs in different scenarios. So if we move back inside the videos directory, I say I want to provide the video 4 as a test directory, and then press enter. And you will observe that a green bounding box has been specified around the traffic light that we want to detect. So the traffic light detection using our trained cascade has been done perfectly for the trained video, but you could also use a test video and see how well it performs in a real environment. But for this case, we can safely say that our training has gone very well, and we can use this hard cascade for detecting the traffic lights. Now, the whole procedure that I've mentioned was specific to a traffic light, but the same process can be followed for any other object that can be handy for detecting using the hard cascade. Now, let's move on to integrating this particular train cascade in our project and see how well it does in our real task that was to cross the intersection based on detecting the traffic lights. Till then, thank you and bye. Hard cascade detection algorithm from scratch. In the current tutorial, we are looking to apply this already trained hard cascade to our project for detection of traffic lights. As I've already done the setup, so let's go over a quick overview. I started off by creating the traffic light detection.py file, which contains the detect traffic light function that actually attempts the core concept of detection of traffic lights. This can be achieved by creating a class of cascade detector, where we load our trained cascade from the data folder and save it inside the traffic light cascade variable. Once we have loaded the trained cascade, we now create a detect function that actually performs the detection of the traffic light by using the trained cascade and simply applying it over the grayscale image. Once we have detected a region of interest, we highlight its location by drawing a nice looking rectangle around it. This completes the coding part, and now before we can build it, we need to first notify the Python of this module's part. So what we do is simply hover over to the setup.py file and simply highlight the traffic light detection module's location and save it inside the packages. Once we have done that, we move over to the terminal, build the project, and run the simulation. This time, you will notice that we launched the main simulation because we are testing for the fourth feature of traffic light detection. Once we have done that, we launch the computer vision node. And as the computer vision node starts up, you will notice that the car is just before an intersection. As this car approaches the intersection, you will notice that it detects the traffic light highlighted by the orange rectangle drawn around that traffic light. Once it detects the traffic light, you will notice that the hard cascade detection algorithm has been trained correctly, and we can proceed on to the next step. Phew, on to the next one. Hard cascade may be very in form, but this might not be enough. In the case of traffic light, we have previously identified that the minimal error or the maximum accuracy was required. In that case, any failsafe is a must. For that reason, we have employed a handcrafted feature classifier as a detection confirmation mechanism. Once we have confirmed what the hard cascade has detected is indeed a traffic light, the next thing required by us is to extract what state is it in. Starting with the confirmation mechanism, following other features that are required to confirm a hard cascade detection as a traffic light. The first thing, or the first feature that is required, is the three circular regions inside the detected region by the hard cascade. These circular regions will be representing the three circular lights of the traffic light. Second are the three distinct colors of red, yellow, green of that three distinct circles. The third feature that is required is that these circular regions should be at a fixed distance from each other, and they should have similar size and be almost parallel to each other. And finally, there should be no intersection between any of these distinct circles. And lastly, the order of the color should always be maintained, that is, red, yellow, and green. Once we have found a particular detection by the hard cascade that has all these features mentioned above, then we can safely say that that detection is indeed a traffic light. For state retrieval, it is easy because we have identified the region of the three circular lights. All we need to do now is to check which light is the brightest, indicating the state of that traffic light. For example, in this particular condition, the red light was the brightest, so the traffic light was indicating a stop condition. In coding terms, we have the detected region of interest, presumably the traffic light, as an input. We pass it on to the confirmation mechanism that tries to determine which state the traffic light is in, if it was a traffic light at all. Otherwise, it would simply return unknown. Hello guys, in our previous meetup, we tested our train hard cascade and it was detecting the traffic light in the simulation. Today, we want to build a confirmation and state retrieval mechanism. The idea is, as you saw in the previous video, the hard cascade is good, but it's not perfect in detecting the traffic light. So we want to create a check system that can first identify whether the detected region of interest is indeed a traffic light and then retrieve its state. For this purpose, we create a class that we name as traffic light states. This class' main purpose is to retrieve the state of the traffic light once we have confirmed a detection. Inside it, the very first thing that we need to do is simply declare a few instance variables. These are of two types. The first are the state variables representing the state of the class, and second is simply the control variable, that is to simply draw all the detected regions. After this, we declare our main function of get traffic light states. This does the main task of state retrieval once it has confirmed a detection of traffic lights. It takes in the arguments of frame and frame growth. It does the state retrieval in two steps. For the first step, it simply isolates or segments the green and the red regions in the whole image because we are simply looking for the green and the red signals of the traffic light. This is done by using color segmentation similar to what we did for the color segmentation of the white and the yellow lanes in the lane detection module. I've already created a separate class for this that I've named as color segmentation.python file. Now, what we simply need to do inside the get traffic light states function is call this function of the color segmented class, that is isolate yellow red regions, and pass in the frame, and this gives us the grayscale of the yellow red regions segmented up. This output becomes the input of the second step, that is the confirm traffic light and retrieve states function. This confirms the traffic light, and then once confirmed, it retrieves the state of the traffic light and passes it as an output. Inside the confirm traffic light and retrieve states function, the very first thing that we need to do is simply confirm the detection to be indeed a traffic light. This will be done in two core steps. For the very first step, what we do is simply isolate all the circular regions in all of the image using half circles. This is done because the circular regions include the circular lights inside the traffic light. Then, once we have isolated the circular regions, we try to compare each circle with all the other, trying to find out the combination that best represents the traffic light. For example, as we discussed in the algorithm, in the theory, we have set a few parameters or features that represents a traffic light. Once we test them out, and one such image or one such region of interest matches that case, then we have detected or confirmed a traffic light. Then, once we have a confirmed detection, we now need to retrieve the state of the traffic light. This is done by simply checking which of the yellow and the red regions are the brightest. For example, if the red region or the red light is the brightest, this indicates the stop condition of the traffic light, otherwise it's the go state. This completes the getTrafficLightStates main function of the TrafficLightState class, and now we can simply import this class as an object inside the cascade detector and create this confirmation and state retrieval mechanism. Once the state of the traffic light has been updated and the TrafficLightState class has been completed, we simply create an object of the TrafficLightState class inside the initialization function of the cascade detector object. This will be named as self.tlStates is equal to TrafficLightStates object. Then move inside the detect function, where we simply declare a few variables that we wish to extract from the getTrafficLightState function of the TrafficLightStates class. For example, the first variable, that is the state of the traffic light, is the direct output that we get from the getTrafficLightState function. Once we encounter a change in the state of the traffic light, we simply set the traffic light confirm boolean variable to true, and the traffic light confirm mask is something that will be used later on. Then before we can pass this information to the confirmation and state retrieval mechanism, we first need to isolate the region of interest by masking out everything else. This gets to be the input to our state or the getTrafficLightState function. Then, once the traffic light state has been found to be changed from unknown to a new state, we simply draw a green rectangle around the traffic light, signaling its confirmation. Then we return all the set variables and simply retrieve them inside the detectTrafficLight function of the main traffic light detection class. Then we simply check if the traffic light has been confirmed. Then we display the message that we have a confirmed sighting of a traffic light. Hooray! We start by building the project and then running the simulation. Once the simulation has run, we can now run the computer vision node. At the start, you will notice a new line that represents the state of the traffic light, which is set to unknown at the initial point. But once this traffic light gets detected by the hard cascade, you will notice a green rectangle representing the confirmation of the detection. And then we will retrieve the state of the traffic light, which is go at this point, and this is the correct state being retrieved. So our confirmation and state retrieval mechanism is now working correctly, and we can proceed to the next step. Till then, thank you and bye. If we have highly accurate method of detecting traffic light, why then would we need to track it? There are two reasons to this. Number one, the detection algorithm that we chose were accurate, but they were not reliable. Meaning, if they did detect something, we can be pretty sure that that was indeed a traffic light. Otherwise, if they did miss something, then that can prove fatal for us, while also losing track of its identity in the process. Also, we did mention that the traffic light had dynamic state. So any traffic light or detection algorithm will struggle to maintain its accuracy. Considering these points, it seemed like a viable solution to start tracking the traffic light once we have confirmed the detection. For tracking the traffic light, we'll be using the same optical flow tracking algorithm by providing it the detected traffic light as an input. Able to track the traffic light, but was it enough? Reviewing the targets that we were trying to achieve, the traffic light detection, the number one target was, where is the traffic light? Tracking helped solve this first problem by tracking the traffic light for the next few frames. The next target was to extract the state of the traffic light. The confirmation mechanism that we developed helped us in this regard of extracting the state of the traffic light. But it required a region of interest. In the case of optical flow, the region of interest was never tracked, rather the points were tracked. So how can we move from the information of tracked points to the tracked region of interest? This was the problem that we need to solve to complete the process of traffic light detection. The solution was very simple: homography computation. In the field of computer vision, any two images of the same planar surface in space are related by homography. In our case, that planar surface is the traffic light. Once the car moves, the traffic light is perspectively transformed. Optical flow tracks that transformation in the form of points. To estimate the homography relation between the initial state and the final state by comparing the move point is essentially what the fine homography does. Once we have computed the homography matrix, we can then move on to draw the track region of interest or the final location of the traffic light. Coding the final piece of the puzzle, we will have the track points from the optical flow tracking algorithm as an input. We will be using homography estimation to estimate the track region of interest as an output. This region of interest will be used to retrieve the state of the traffic light, continuing the process until tracking fails. We developed the confirmation and the state retrieval mechanism that helped us to test the authenticity of the hard cascade and also retrieve the state of the traffic light. Now the question is, will this be enough for the car to act timely while navigating the intersections? Of course not. A better approach would be to track the traffic light once we have a confirmed detection, and only then can we retrieve the state of the traffic light with confidence on every frame. So in this section, we'll be using the same tracking system that we developed for science, but with slight modifications. So for this purpose, we need to import the tracker class that we developed earlier from the optical flow tracking.py. So what we do is simply write here, from optical flow tracking, import the track class. Now this tracker class will become the parent class to the tracker child class that we wish to make for this traffic light detection. So we write here class TL tracker and pass in the tracker as the object. So this becomes, the TL tracker becomes the child class to the parent class of tracker. And it has inherited all the functionality of its parent class that includes the member functions and the member variables of the parent class. And now if you wish to add any new functionality, we can simply do that by writing, for example, I wish to add a new functionality to initialization function. So we write initialize, and what this gives me is super.init. So what the super keyword does is simply takes the functionality of its parent class and also provides it to the child class. So if I want this inside this child class, I leave it as it is, otherwise I omit this particular line. And now I add in the new functionality that I wish to add for this child class function. That is, that I want to initialize two new instance variables. These are the track region of interest mask and the collision imminent Boolean variable. Now the first variable that we have initialized, or the instance variable that we have initialized, is basically the track region of, or the mask of the track region of interest. And second is the collision imminent, which is basically the proximity between the car and the traffic light. And at the moment, it is initialized to false. And now, once we have done this, we can now initialize the second function, particularly the second function for this child class. That is init tracker. Now the init tracker, like the initialization function, also uses the same functionality of its parent class by calling super.init tracker. But along with this, we also reset the instance variable that we just declared inside the initialization function. And that can be done by simply writing self.track region of interest mask and passing in the mask to track that is the argument of this particular function. Apart from this, the collision imminent has been reset to false because this tracking function has been initialized at this moment, which gives us a clue that the car is not very close to the traffic light as of this moment. Now, we define the third function for this particular class, that is the traffic light tracker. That is the track function. Now, the track function is the core function that performs the tracking for the optical flow tracking algorithm. Now, because we want the functionality slightly modified for this track function, so we cannot directly inherit it from its parent class. So what we do is known as function overriding. Now, function overriding simply means to redefine the function inside the child class of its parent class, and that is done by slight modification. So let's do that. So I write here definition track. Now, instead of doing the same thing that we did earlier, I provide in the new arguments. That is, this time we have the image instead of the gray, and I have the frame draw. And then, instead of calling in super or using the same functionality of its parent class, I define the new functionality. Now, the first thing I need is that I want the same functionality, slightly the same functionality of its parent class. So I go over to the optical flow tracking and then simply copy over this track function. So I write Control-C and paste it here. Once I've copied it over, you will notice a few errors. The first error is that the grayscale has not been initialized. Now, the grayscale is not present because instead of the grayscale as the input argument, we now have the BGR. So we need to convert this BGR color space to the grayscale, so this can become the input to calculate optical flow pyramidal Lucas Ginat. So let's do that. So what we do is simply convert the image to the grayscale and pass in that argument to the calculate optical flow pyramidal Lucas Ginat algorithm that actually performs the tracking for this algorithm. Once it tracks the old point to this new point, that is P1, we extract the good old and the good new points. Once we have that, we now want a new functionality that we want to add inside this function. Now, instead of just drawing these points out for this particular tracker, we want to estimate the track region of interest from these track points. The reason we want the track region of interest instead of the track points is because the track region of interest will be used to estimate or get the state of this traffic light. And that will be done using homography estimation. So let's define that particular function that will be doing the homography estimation using these good new and the good old points. So we go up here, right here, estimate track rect. So we pass in the point source and the point destination and the image draw, and then define is this function. For the very first thing, what we do is simply set the self.mode to tracking because we are inside the tracking mode. So we set the mode of this tracker to tracking. And also we check the point source to be greater than 3. Why are we checking this point source to be greater than 3? Is because that when we want to do the homography estimation, that requires at least 4 points to estimate the homography matrix. And if we don't have those 4 points, then we cannot proceed inside this function. So if we have this greater than 3 points, that means represent 4 or greater points, we can perform the next step. For the next step, what we need to do is simply declare a new function that will be called inside this if length point source greater than 3. That function will be known as sanitize points. And what this function will do is simply use the point source and the point destination, taking the point source and the point destination, and order them out in their strength. That means that the closest points that were present in the previous frame to the current frame are simply ordered from in the descending order. So let's define that particular function right over here. That function is the sanitize points. It takes in the point source, the point destination, and simply outputs the strongest points in the descending order. So the first few points are the strongest points. So and that are the points that we wish to extract. So we simply go over right over here, call that sanitize point function, and then what we receive are the strongest point in the descending order, and we simply extract the top 4 points. Once we have those top 4 points, we can now estimate the homography matrix, which will be used to estimate the new track region of interest. So let's do that. So we use that point source and the point destination, strongest point source and point destination, to get the affine transform, which estimates the homography matrix, and then use that homography matrix to simply warp or transform that previous image or previous mask into the new mask that represents the track region of interest. Once we have done that, we now have the mask, and now we can proceed on to the next step. For the next step, we simply define the region of interest that we have extracted previously using warp affine. And by refining, I mean I simply remove the noise, that is small noise, and also connect the disconnected portions. And then once we have that defined track region of interest, we do the fourth and the final step in this particular function, that is estimating the proximity of the car to the traffic light. And that is done by simply checking a few conditions. And when the proximity is less than the desired outcome, then we can simply write here that the collision imminent to true. which means that the car is very close to the traffic light. So the collision imminent means that the car is about to collide to the traffic light or about to cross it. Once you've done that, I can simply move on to the next step. For finally, in this function, we need to address the case where the points are less than 3. So there can come a point where the points are less than 3. So that means we cannot estimate the homography matrix, so we cannot proceed in this function. For this case, we simply reset the tracking to, or mode of the tracker to detection and reset the rest of the variables, that is the track region of interest mask and the collision imminent to false. And once we've done that, we are finished with this particular function and we can call it inside the track function. So right after we have extracted the good, new, and old points, we call that particular function of estimate track. This gives us a track region of interest mask, and after drawing all the tracking track points, we perform the last step for this track function. And that will be to simply estimate the track region of interest from that track region of interest mask. So we use that mask to get the region inside the image, inside the whole image, which represents the track region of interest. This track region of interest will be returned to the user to be used to estimate the state of the traffic light. So this completes our new child class, that is the traffic light tracker, that will be used to track the traffic light once it has been confirmed to be one. So let's add it or connect it to our whole mechanism and see the results. Perform detection and then retrieve the state of the traffic light. So now we incorporate the tracking process once we have a confirmed detection. For that, we need to create an object of the traffic light track class, which we write as TL tracker parentheses. So this creates an object of this class, which we name as TL tracker underscore. Once we have created its object, and inside, once we have a confirmed detection, we can now call its function of the tracker class, that is initialize tracker, to basically initialize the tracker because we have confirmed detection. And that can be written as TL tracker underscore dot init tracker. We pass in the first argument, which is the label, which is basically the current traffic light state. Second, as gray. For the frame to draw, we pass in image draw. And for the start and end point, we pass in none, because we are instead passing in the mask to track. And for the mask to track, we pass in the traffic light confirm mask, which was received from the detection process. So this is basically the mask or the region to track. Once we have initialized our tracker, the second thing that we need to cater for is, because all this process that we have done inside this function is part of the detection process, so we need to enclose it inside the condition that this tracker should be in the detection mode. So let's do that. So we simply enclose this inside the condition. The TL tracker mode should be detection. And once it is in the detection mode, perform the process that we did below. Otherwise, if it's not in detection mode, this means that it's in the tracking mode. So we need to call the track function of the TL tracker. So this track function takes in the argument of image and the frame draw, which is basically the image draw. So once we perform the tracking using the track function, this gives us or provides us the region of interest that is being tracked. So we write it as track region of interest as the output of the track function of the TL tracker. Once we have this region of interest tracked, we can now retrieve the state of the traffic light using the function getTrafficLightState, which is basically part of the traffic light state class. So we need to create an object of that class to access its function. So let's create an object of the TL states class. We write TL states parentheses, which creates this object, and name it as TL states underscore. Once we have created this object, after we have tracked the region of interest, we can now call this TL states object and call its function of check traffic light state. This takes in the track region of interest as a frame, because this is the region which is used to check the traffic light state or update the traffic light state, and then pass in the image draw as a frame to draw. Once we have done this, the traffic light state has been updated by this particular function by checking it inside the track region of interest. So now we can retrieve it and save it inside the current traffic light state. So we write TL states dot traffic state. So the current traffic light state has been updated once again inside the tracking process, and this was updated inside the detection process too. So whatever this is, we return it in the end. Along with this, whatever the traffic light state is, if it is not unknown, we basically display that to the user so that the user can analyze. And lastly, we return the state and the proximity status of the traffic light to be received at the driveboard.py. So once we have returned this, we move over to the driveboard.py, save this, move over to the driveboard.py, and just receiving the traffic state before, we now receive the proximity status. So now that we have the proximity status and the traffic state, we can now simply pass it on to the display state 2 to display to the user. Once you have done this, our traffic light detection process has been completed. To test it, we move over to the terminal, build the project, launch the simulation, and once the simulation starts up, we run our computer vision node. And once the computer vision node starts up, you will notice once the car approaches the traffic light, the car not only detects and retrieves the state of the traffic light, but it also starts tracking the traffic light once it has a confirmed detection, so which you can see right here. So this improves the reliability of the system, which means that we can now proceed on to building its control system so that we can leverage the information that we have just received. Till then, thank you and bye. Then we check for the mode of the traffic light detection algorithm, which is initialized to detection. Then, once in the detection stage, we check for the available traffic light by using trained hard cascade algorithm. If found, we pass it on to the confirmation mechanism that once confirmed, retrieves the state of the traffic light. Otherwise, the next frame is extracted and the detector is applied once again. If a particular traffic light has been detected and its state is retrieved, then the mode of the traffic light detection algorithm is now set to tracking. Then once in the tracking stage, the optical flow tracking algorithm tracks the traffic light in the next few frames. In each of these tracked frames, the region of interest of the traffic light is retrieved using homography, and its state is extracted in the next frames. This process continues until the tracking algorithm fails. If it does fail, then the traffic light detection algorithm reverts back to its original position, and the cycle repeats. The traffic light detection stage means we have the input for the fourth and the final feature of our self-driving car, that is, to cross the intersections. Right at the moment when it was required, using this information, the self-driving car will try to cross the intersection by stopping at red light and moving at green. And following are the two constraints that we will be facing while developing this rule-based algorithm. Starting with the first constraint, that is, we are considering only to keep the lane in which the car was moving. For the second constraint, no path planning is incorporated here. So in short, the car will keep following its lane, stop at red light, and move at green. Fourth and the final feature is of crossing intersection. The info that we got from the traffic light detection was the state of the traffic light and the proximity of the traffic light to the self-driving car. Following are the considerations we need to make before putting forward our proposed algorithm. Starting with the first consideration, that is that the traffic light can attain one of three states that are red, yellow, and green. For the second consideration, if the traffic light attains a stop sign and it is close to the self-driving car, then the self-driving car should simply stop. For the final consideration, we are only concerned with crossing the intersection and not navigating for simplicity. For the proposed algorithm, we start off by defining the rule for the case where the car has encountered a traffic light with a red state and is nearing it. Here, we perform two things. Number one, activate the stop mode and set the car speed to 0. Then once in the stop mode, if the state changes to go, then we activate the go mode and deactivate the stop mode. Now we need to define what happens when the go mode is activated. When the go mode is activated and the previous mode was stopped, then the self-driving car moves straight for n iterations until it has crossed the intersection. Then, when the n iterations has expired, then we deactivate the go mode and the intersection has been successfully crossed. Coding the algorithm described previously, we have the state of the traffic light and its proximity as an input. And for an output, we have the speed and the angle parameters of the car. In this way, the car was successfully able to cross the intersection. Hi guys, previously we did the first part of that is traffic light detection. Now we do its second part, that is building the control system to act upon this received information. For this purpose, we pass in the traffic state and the proximity status to the control system as the current state of the car. Then, inside the drive function of the control system, we unpack the current state as in traffic state and the proximity status. Then we call in the function to actually perform the navigation. This will be obey traffic lights. This takes in two arguments of traffic state and the close proximity. Now before defining this function, we first declare a few variables inside the initialization function of the control class. The first two are basically the state of the feature, and second or third one is the timer. Now we simply define the function that will perform the navigation, that is obey traffic lights. Here, the very first thing that we do is check whether the car has approached a traffic light which is in red condition. In such a condition, we stop the car and activate the stop mode. Otherwise, we only proceed if the car was already navigating the intersection, which means it was either in the stop mode or in the go mode. Inside, if the car was stopped because of red and now the traffic light has turned green, then we deactivate the stop mode and activate the go mode. Otherwise, if the car is already in the stop mode, then we maintain 0 speed for the car. Or if the car has finally entered the go mode, then the car starts crossing the intersection. This requires ignoring the lane assist and moving straight for a fixed period of time until the car has crossed or navigated the intersection. Now that we have completed the rule-based control system, let's test it by navigating to a terminal and building the project. Here, you will see as the car approaches the traffic light that has a red condition, the car will stop. And then the car will only move once the traffic light turns green. And once it turns green, the car will move straight, ignoring the input from the lane assist feature for a few moments. And then once a fixed time has elapsed, the car will have finally crossed the intersection. This means that the fourth and the final feature of crossing intersection has now been completed. So a big thumbs up to you guys on a job well done. Starting with a self-driving car or car with no self-drive features, we have now created a level 3 self-driving car with 4 key features. So I hope you got to learn a lot of new stuff, brush up on the old, and leveled up as a self-driving car engineer. That's it for this course. Happy driving. Bye. Science. Using this information, we were able to develop rule-based control algorithm to provide our self-driving car with the following 4 features: the ability to lane follow, cross intersections, cruise control, and navigating T-junction. With this, we conclude the development of our level 3 self-driving car, and now let's run the whole process to see each of the features in action.